Imagine a universe that stretches out before us, a vast expanse brimming with secrets that are as deep as they are infinite. Every star, every shadow, and every shimmering nebula holds a story, a piece of the cosmic puzzle just waiting to be discovered. The phenomena of this universe are far beyond our comprehension, each one more perplexing and awe-inspiring than the last. From the enigmatic realms of black holes, those colossal cosmic giants that devour everything in their path, to the elusive, invisible forces of dark matter and dark energy that shape the very fabric of the cosmos, the universe reveals its mysteries to us slowly, relentlessly. Even though we cannot see these forces with our naked eyes, their presence is undeniable, shaping the very existence of galaxies and stars. On this journey, we delve into the heart of these phenomena, exploring neutron stars that spin with mind-boggling speed, fierce quasars that outshine entire galaxies, and the hauntingly beautiful mysteries of exoplanets located light years away from our solar system. As we venture into these uncharted territories, we unlock the stories of the most mysterious objects in the universe, objects that seem to exist on the very edge of our understanding. Our fascination with the universe stems from more than just an intellectual curiosity. It is rooted in a deep, almost primal sense of wonder and an inherent desire to understand our place in the vast expanse of space. This desire to explore, to answer questions that have plagued humankind for millennia, is not just about finding the answers, but about the thrill of the discovery itself. The universe, with its infinite complexity and unexplained phenomena, challenges the boundaries of science, forcing us to reconsider what we know about time, space, and reality. Humankind's urge to explore the unknown has always been intertwined with a recognition that even the smallest detail, whether it be a grain of stardust or the spin of a distant planet, may connect us to something far greater. The exploration of galaxies, the study of black holes, or the search for life on other planets, all of these questions open up a world of possibilities, each one as tantalizing and perplexing as the last. Each discovery, whether monumental or minute, only deepens our thirst for understanding, sparking new questions about the origins of the universe, the mechanics of cosmic events, and what lies ahead for humanity in relation to the stars above. The unknown holds an allure like no other. It represents the possibility of adventure, of something out there waiting to be discovered. Space exploration is not merely about the pursuit of knowledge. It is a manifestation of human resilience, of our constant drive to push the boundaries of what we know, to dream of a future where we might one day travel beyond the confines of our home planet. This drive, fueled by an innate curiosity and the limitless potential for exploration, binds humanity to the mysteries of the cosmos. Every time we look up at the stars, we are reminded of how much is yet to be uncovered. And it is in that pursuit of the unknown that we find purpose, excitement, and a sense of wonder. The quest to understand the most mysterious objects in the universe has shaped human history in profound ways. It has spurred scientific advancement, ignited revolutions in thought, and driven humanity to achieve feats once thought impossible. From the earliest times, when our ancestors first gazed up at the night sky, celestial bodies have captivated human imagination. Ancient civilizations, such as the Babylonians and the Egyptians, closely observed the movements of the stars and the moon. These observations were not merely for academic curiosity. They were essential to the development of calendars, agricultural practices, and religious rituals, all of which were tied to the celestial rhythms of the sky. This early fascination with the heavens laid the foundations for what would become one of the most profound sciences, astronomy. What began as a mystical, religious endeavor slowly evolved into a discipline grounded in observation and inquiry. The Greek philosopher Aristotle, for instance, proposed groundbreaking ideas about the cosmos, which set the stage for centuries of thought about the nature of the universe. These early ideas, however, were only the beginning. It was not until the work of Copernicus that our understanding of the cosmos truly shifted. Copernicus's heliocentric theory, which proposed that the Earth orbits the Sun, revolutionized not only science, but society itself. This paradigm shift challenged the Earth-centered view of the universe, shaking the foundations of religious beliefs and societal norms. It set in motion a wave of scientific inquiry that would ultimately lead to the scientific revolution. With the invention of the telescope in the early 17th century, humanity entered a new chapter in its quest for knowledge. The first observations of distant stars, moons, and planets revealed a universe far more complex and unpredictable than anyone could have imagined. Galileo's groundbreaking discoveries, such as the moons of Jupiter, began to dismantle the myth of a perfectly ordered celestial realm. Instead, what we found was a universe full of chaos and unpredictability, a place where new phenomena were constantly being uncovered. This revelation ignited a feverish curiosity that spurred further exploration, each new discovery unveiling another layer of the cosmic mystery. As we journey through this uncharted space, we encounter objects and phenomena that continue to challenge our understanding of the universe. The discovery of Saturn's rings, or the moons of Jupiter, sparked a technological and mathematical revolution, leading to advancements in telescopic design, space exploration, and theoretical physics. These breakthroughs, one after the other, have continuously expanded the horizons of what is possible. Today, we stand at the edge of a new frontier. Our understanding of the cosmos has advanced beyond our wildest dreams, yet the universe remains a vast and mysterious expanse. The more we learn, the more we realize how much we still have to discover. Whether it's studying the unyielding power of black holes, deciphering the strange behavior of distant stars, or searching for life in the endless sea of exoplanets, the journey is far from over. And so the quest for knowledge continues, as we seek to unlock the mysteries of the universe and understand our place within it. Every discovery is not an endpoint, but another step forward on an eternal journey, one that invites us to explore, question, and ultimately, dream. The study of enigmatic cosmic objects like black holes and dark matter has become one of the most compelling frontiers of modern science. These phenomena are not merely subjects of intrigue. They are forces that drive the development of new theories, instruments, and methodologies. As we push further into the vast unknown, we are confronted with questions that defy the limits of human understanding, demanding inventive solutions. The quest to unravel these cosmic mysteries compels us to devise ever more sophisticated instruments, telescopes powerful enough to peer deep into the fabric of space, and particle accelerators capable of revealing the very building blocks of matter. Moreover, the pursuit of understanding these elusive entities extends far beyond the realm of science alone. It profoundly shapes our cultures, philosophies, and collective identity. As we explore the nature of the universe, we are forced to reconsider our place within it, sparking reflections on existence, time, and space itself. This journey of discovery is a deeply collaborative effort, one that unites scientists across geographical, disciplinary, and even ideological boundaries. It fosters an unprecedented sense of shared purpose and unity, as researchers from different corners of the globe work in concert, each contribution building upon the other in the pursuit of answers to the universe's most profound questions. In this shared endeavor, we also witness the tremendous power of human ingenuity. The development of groundbreaking technologies, such as advanced telescopes that can capture light from the farthest reaches of space, or particle accelerators that probe the most fundamental forces of nature, stands as a testament to our creative capacity. These tools serve as the bridges between the known and the unknown, enabling us to examine objects in space that, until recently, were only the stuff of science fiction. As we peel back the layers of cosmic mystery, we are also confronted with the inherent challenges of our understanding. Black holes, neutron stars, dark matter, and quasars. These are but a few of the enigmatic phenomena that continue to captivate the imagination of both scientists and the general public. Each of these objects presents its own unique set of challenges, revealing not only the limits of current scientific knowledge, but also the vastness of what still remains to be discovered. One of the most perplexing and intriguing of these objects is the black hole, a region of space where the gravitational pull is so intense that not even light can escape its grasp. These cosmic giants, formed when massive stars collapse under their own gravity, defy our most fundamental understanding of physics. What makes black holes so mysterious is not just their gravitational force, but the fact that they do not emit any detectable light or radiation. They are, in a sense, invisible, their presence only inferred by the way they influence nearby objects such as stars and gas clouds. To truly understand black holes, we must venture into the realm of the impossible. Theoretically, inside a black hole lies a singularity, a point of infinite density where the known laws of physics break down completely. This concept challenges our fundamental understanding of space and time. Around a black hole lies the event horizon, a boundary beyond which nothing can return. This boundary marks a point of no escape, where the very fabric of spacetime is stretched and distorted by the immense gravity of the black hole. The closer you get to the event horizon, the stronger the gravitational pull, and the more time itself begins to slow down. At the event horizon, time stretches out infinitely, creating a fascinating intersection between gravity and the passage of time. Yet, despite decades of theoretical work and technological advancement, much about black holes remains a mystery. How exactly do they form? What occurs inside them beyond the event horizon? What happens when two black holes collide? These questions continue to elude scientists, pushing the boundaries of our understanding further with each discovery. As we explore these enigmatic objects, we also delve into the nature of neutron stars, another captivating phenomenon. Formed from the remnants of massive stars that have exploded in a supernova, neutron stars are some of the densest objects in the universe. A teaspoon of neutron star material would weigh as much as a mountain on Earth. Such is the compression of matter that occurs during their formation. These stars rotate at staggering speeds, and their intense magnetic fields can produce beams of radiation that sweep across the universe like cosmic lighthouses. Some of these neutron stars, known as pulsars, emit regular bursts of radiation, allowing scientists to study them like celestial clocks, providing a wealth of information about the nature of space and time itself. Beyond these stellar remnants, dark matter looms as one of the greatest mysteries of the cosmos. While we cannot observe dark matter directly, its presence is inferred from the gravitational effects it has on galaxies and galaxy clusters. Scientists believe that dark matter constitutes a significant portion of the universe's mass, yet its exact nature remains elusive. This unseen force appears to influence the movement and interaction of galaxies, raising profound questions about the structure and composition of the universe itself. Quasars, another enigmatic phenomenon, present yet another challenge to our understanding of the universe. These extraordinarily bright and energetic objects are powered by supermassive black holes at the centers of distant galaxies. Despite being located millions or even billions of light years away, quasars can outshine entire galaxies, providing a glimpse into the early stages of the universe. Their study offers valuable insights into the formation and evolution of galaxies, shedding light on the most distant and ancient corners of the cosmos. Then there is the possibility of extraterrestrial life. The search for habitable planets beyond our solar system, known as exoplanets, continues to captivate the human imagination. As we discover more about these distant worlds, we are forced to question what defines life, how it arises, and whether we are truly alone in the universe. The search for life beyond Earth is not just about finding alien life forms. It is about understanding the nature of life itself and our place in the vast cosmic expanse. Each of these mysterious cosmic objects offers a tantalizing invitation to explore the universe in ways that challenge our preconceptions and expand our understanding of reality. As we look outward into the cosmos, we are reminded that there is still so much we do not understand. Yet, in this uncertainty lies the very essence of scientific discovery, the relentless pursuit of knowledge, and the unyielding drive to answer the questions that define our existence. The study of black holes, neutron stars, dark matter, quasars, and the search for alien life continues to fascinate and inspire. These phenomena offer not just intellectual challenges, but existential ones, urging us to reconsider what we know about space, time, and life itself. As we continue to gaze upward, driven by curiosity and wonder, we are reminded that the pursuit of knowledge is not just a scientific endeavor, it is a deeply human one, shaping our identities, driving technological innovation, and inspiring future generations to look toward the stars. This cycle of exploration and discovery has come to define humanity's greatest achievements, propelling us forward into an uncertain but undeniably thrilling future. In the vast and mysterious universe, there exist fascinating cosmic entities that challenge our understanding of space, time, and gravity. black holes. These enigmatic objects come in various sizes and forms, ranging from stellar black holes, which are a few times the mass of our Sun, to the colossal supermassive black holes found at the centers of galaxies, with masses reaching millions or even billions of times that of our Sun. Yet, there is a class of black holes that remains somewhat elusive: intermediate black holes. Intermediate black holes exist in the space between stellar and supermassive black holes, both in terms of mass and influence. Their existence is far more mysterious because they are significantly harder to observe. These mid-sized black holes are thought to form in dense star clusters where stars are packed tightly together, creating the conditions for these black holes to emerge. However, identifying these objects remains a challenge for astronomers. Their elusive nature means scientists are actively exploring ways to understand how they fit into the grand structure of the cosmos. Despite this uncertainty, the study of black holes, whether stellar, intermediate, or supermassive, continues to be a key area of research, offering profound insights into the universe's most fundamental forces. When we look at the role of black holes in the cosmos, it is impossible not to be drawn into their strange and captivating characteristics. Black holes offer a window into the very fabric of space and time. Their study helps us probe the mysteries of gravity, the life cycles of stars, and even the nature of space itself. Each type of black hole, whether it's stellar, intermediate, or supermassive, plays a distinct role in shaping the cosmos, contributing to a cosmic tapestry that both captivates and challenges our curiosity. One of the most intriguing features of black holes is their event horizon. This is the boundary beyond which no light or matter can escape. Once light crosses this threshold, it is pulled inexorably inward by the black hole's gravity. To help visualize this, imagine a deep well so steep and narrow that no matter how hard you try, it becomes impossible to climb out. The event horizon is like the edge of this well. Once light passes this boundary, it is trapped within the black hole, unable to find its way back to the universe. In this region, space itself becomes warped, with the curvature of space-time becoming so extreme that every possible path leads deeper into the black hole. For light, which always travels at the fastest possible speed, the event horizon acts as a one-way street. Once it crosses this boundary, there is no turning back. Think of it like a roller coaster cresting the top of a steep hill. Once the coaster tips over, it is committed to the downward plunge. In much the same way, light that crosses the event horizon is pulled in, unable to reverse its course. This phenomenon is why black holes are often described as black, because no light can escape, rendering them invisible and mysterious to us. This characteristic makes black holes some of the most intriguing and puzzling objects in space. The discovery of gravitational waves, ripples in the fabric of space and time, has revolutionized our understanding of the universe. Gravitational waves are generated when massive objects, like black holes, accelerate and collide. Imagine dropping a stone into a pond. The ripples that spread outwards are similar to the gravitational waves that travel across the universe. These waves carry with them vital information about their origins, providing a new way to study cosmic events. When scientists first detected these waves, they confirmed a key prediction of Albert Einstein's theory of general relativity. This theory describes gravity not as a force, as previously thought, but as the bending of space and time by mass. The detection of gravitational waves has provided astronomers with a new tool. Rather than relying solely on visible light and traditional telescopes, they can now listen to the universe through these ripples in space-time. This breakthrough has opened up new possibilities for observing cosmic events that were previously invisible to us. One of the most profound applications of gravitational wave detection has been in the study of black hole mergers. When two black holes spiral toward one another and merge, they produce gravitational waves that carry crucial information about the properties of the black holes involved, such as their masses and spin rates. These events offer researchers valuable insights into the formation and behavior of black holes, providing clues about their rates of occurrence and distribution in the universe. The study of black hole mergers has also led to the emergence of a new field in astrophysics, multi-messenger astronomy. This approach combines information from multiple sources, gravitational waves, electromagnetic radiation, such as light, and particles, to create a more comprehensive understanding of the universe. By observing these cosmic events from different perspectives, scientists are able to unlock secrets about the universe that were once hidden from us. The detection of gravitational waves, however, is not just a technical achievement. It represents a monumental step toward unraveling the complex structure of the cosmos. These waves provide us with a new way to explore some of the most extreme and violent processes in the universe, offering a deeper understanding of the fundamental laws that govern the behavior of the universe itself. Even though black holes do not emit light that we can directly observe, scientists have developed ingenious methods for detecting and studying them. One of the most common methods involves observing the effects of a black hole's immense gravity on nearby stars and gas clouds. When a black hole pulls in material from a nearby star, it forms an accretion disk, a swirling disk of gas and dust that spirals inward toward the event horizon. As this material heats up to extreme temperatures, it produces intense X-ray radiation, which can be detected by telescopes on Earth. This process allows scientists to observe the presence of black holes indirectly by studying the radiation emitted by the accretion disk. In addition to this, astronomers look for stars that orbit invisible objects, using their movement to infer the presence of a black hole. If a star's motion is influenced by an unseen mass, it can indicate the presence of a black hole. If the star is orbiting a point in space where no visible object can be found, it strongly suggests that a black hole is lurking in that region. This method provides crucial evidence of black holes, particularly those that are not actively accreting material and therefore do not emit radiation detectable by traditional methods. Perhaps the most exciting future development in black hole research is the ability to directly capture images of black holes. Using powerful telescopes, scientists are working toward capturing the shadows of black holes as they are cast against the bright backdrop of their accretion disks. This breakthrough could provide a detailed, direct image of a black hole, offering us a glimpse into the heart of these mysterious objects. In addition to their intriguing properties, black holes play a crucial role in the evolution of galaxies. At the center of many galaxies lies a supermassive black hole, exerting an immense gravitational pull on the stars, gas, and dust around it. These black holes are not passive. They actively influence the dynamics of their host galaxies. As matter spirals toward the black hole, it forms an accretion disk, which can heat up to enormous temperatures and emit vast amounts of energy. This process can cause the accretion disk to outshine entire galaxies, offering researchers a powerful tool to study black holes and their impact on the galaxy as a whole. Through the study of black holes, scientists have gained invaluable insights into the fundamental forces that shape our universe. These objects are not only fascinating in their own right, but are also key to unlocking many of the universe's deepest mysteries. From their role in the formation and growth of galaxies to their ability to bend space and time itself, black holes continue to captivate and challenge our understanding of the cosmos. Black holes, those enigmatic and dense regions of space-time, are not just cosmic oddities. They are essential players in the intricate dance of galaxy evolution. They govern far more than their immediate surroundings, with their gravitational influence extending over vast distances. One of the most fascinating ways black holes impact the universe is by regulating the formation of new stars within galaxies. When a black hole swallows a significant amount of matter, it can unleash an extraordinary release of energy. This energy often takes the form of powerful jets or winds that can expel surrounding gas from the black hole's vicinity. This outflow of material serves as a cosmic barrier, pushing away the gas that would otherwise collapse into new stars. This process slows the rate of star formation, offering a vital check against the possibility of galaxies becoming overly saturated with stars too quickly. This phenomenon of feedback plays a critical role in the long-term development of galaxies. Without such regulation, galaxies could become dense and chaotic, rapidly burning through their available resources. Instead, black holes serve as regulators, maintaining a delicate balance in the galaxy's growth over the span of billions of years. The dance between galaxies is a dynamic one, with galactic collisions and mergers being a common occurrence in the vast expanse of the universe. When two galaxies collide, their central black holes often draw closer to one another, eventually merging into a supermassive black hole. This process not only results in the formation of a larger black hole, but also redistributes energy and matter throughout the galaxy, influencing its structure and dynamics in profound ways. The merging of black holes is one of the most dramatic events in the cosmos, reshaping the entire galaxy and impacting its long-term evolutionary trajectory. In essence, black holes act as the engines that drive the evolution of galaxies. Their ability to shape star formation rates, control the arrangement of stars and gas, and ultimately influence the destiny of the galaxy itself places them at the very heart of cosmic evolution. They are intricately woven into the fabric of the universe, affecting its structure, its life cycle, and even the fate of the galaxies they inhabit. Understanding their role is crucial to understanding the universe itself, as black holes are not just passive bystanders, they are active participants in the ongoing saga of cosmic history. As we venture deeper into the cosmos, we encounter another mysterious force that shapes the universe's architecture: dark matter. Dark matter, as its name suggests, is an invisible substance that constitutes a significant portion of the universe's total mass. Although it cannot be seen directly, scientists have inferred its existence through its gravitational effects on visible matter, such as stars and galaxies. To visualize this, imagine a large stadium filled with a crowd. While you can only see the players on the field, the crowd, representing dark matter, exerts a powerful influence over how the players move and behave, despite being invisible. This analogy captures the essence of dark matter. It is unseen, but its impact is undeniable. The concept of dark matter was first introduced in the early 20th century by Swiss astronomer Fritz Zwicky, who was studying the Coma Cluster, a group of galaxies. Zwicky noticed something peculiar. The galaxies within the cluster were moving at such high speeds that, based on the visible mass, they should have been flying apart. To explain this anomaly, he proposed that there must be an unseen mass providing additional gravitational pull to keep the galaxies together. This was the first suggestion of dark matter's existence, and subsequent observations only strengthened this hypothesis. For instance, scientists discovered that stars at the edges of galaxies were rotating much faster than expected based on the visible mass alone. This indicated that a larger invisible mass was exerting a gravitational influence. Over time, evidence supporting the existence of dark matter has continued to accumulate. From the behavior of galaxy clusters to the cosmic microwave background radiation, multiple independent lines of research have converged on the conclusion that dark matter is a real and crucial component of the universe. Today, scientists estimate that dark matter makes up about 25% of the universe's total mass. While this might seem like a substantial amount, dark matter remains a profound mystery. Unlike ordinary matter, such as the stars, planets, and even ourselves that emits light and radiation, dark matter is completely invisible. It does not interact with electromagnetic radiation, which makes it impossible to detect through traditional methods like telescopes. However, the effects of dark matter are visible in the way galaxies behave. Imagine a galaxy as a swirling mass of stars, gas, and dust. While we can easily observe the bright, visible portions of these galaxies, the bulk of the mass that holds the galaxy together is hidden from view. Researchers believe that dark matter forms a vast, invisible halo surrounding galaxies, helping to keep them intact and influencing their rotation. The speeds at which stars move within galaxies suggest that there is far more mass present than what we can observe with our eyes. This gravitational influence is one of the strongest pieces of evidence for the existence of dark matter, pointing to its central role in the structure of the universe. Yet, dark matter is not confined to individual galaxies alone. It appears to exist in vast clusters that span enormous distances, known as galaxy clusters. Within these clusters, dark matter exerts a powerful influence over the formation and movement of galaxies, altering their dynamics in ways that are still not fully understood. The presence of dark matter reshapes our entire understanding of the universe, hinting at an invisible web that stretches far beyond what our most advanced telescopes can reveal. It forces us to confront the reality that there is far more to the universe than meets the eye, and that much of it remains hidden in the shadows. Despite its significance, dark matter remains one of the greatest challenges in modern astrophysics. Scientists are eager to uncover the true nature of this mysterious substance, but doing so is no easy task. Researchers have proposed several theories about what dark matter might be made of, each offering a different perspective on its elusive characteristics. One of the leading theories suggests that dark matter is composed of weakly interacting massive particles, or WIMPs. These hypothetical particles are thought to have a significant mass but interact very weakly with regular matter. This weak interaction is what makes dark matter so difficult to detect. It neither emits light nor absorbs it, remaining completely invisible to our current detection methods. Another theory posits that dark matter could be composed of axions, lightweight particles that were theorized to exist as part of certain models in particle physics. Axions could be abundant throughout the universe, creating the gravitational effects we observe as dark matter. If axions exist, they might produce observable signals under specific conditions, giving scientists a potential means of indirectly studying them. Finally, there is the possibility that dark matter might consist of primordial black holes, small black holes that could have formed in the moments following the Big Bang. These black holes would be much smaller than the supermassive black holes found at the centers of galaxies, and their gravitational influence would be detectable even though they emit no light. Each of these theories presents an intriguing possibility, but none have been definitively proven. As such, dark matter remains one of the most tantalizing mysteries in modern science. Its invisible presence shapes the universe in ways we are only beginning to understand, guiding the development of galaxies, stars, and even the cosmos itself. The search for dark matter continues to push the boundaries of our knowledge, and with each new discovery, we inch closer to unraveling the secrets of the universe's most elusive substance. The exploration of the universe's most elusive and mysterious phenomena has led scientists down a fascinating and often bewildering path. Among these enigmas, dark matter and dark energy stand out as two of the most profound challenges to our understanding of the cosmos. Both of these forces, despite being invisible and undetectable by conventional means, play a crucial role in shaping the structure, evolution, and ultimate fate of the universe itself. In recent years, researchers have proposed groundbreaking theories that challenge our long-held perceptions of gravity, potentially reshaping how we interpret the very forces that govern the universe. One such theory suggests that dark matter, the unseen mass that exerts a gravitational influence on galaxies, might not be the result of hidden particles at all, but rather a misinterpretation of how gravity behaves at large scales. According to this hypothesis, our understanding of gravity could require significant modifications, particularly in how it operates across the vast expanse of the cosmos. If this theory proves correct, dark matter may not exist in the traditional sense at all. Instead, what we perceive as visible matter may simply be a consequence of a new type of gravitational interaction that we have yet to fully comprehend. While none of these radical ideas have been conclusively proven, the ongoing experiments and observations conducted by scientists are providing critical insights, slowly unraveling the mysteries that have baffled astronomers for decades. At the heart of this mystery lies the question of how gravity behaves on the largest scales. Could the gravitational forces we observe simply be the result of unknown interactions, or is there something fundamentally different happening across vast stretches of space and time? With every new experiment and observation, we are edging closer to understanding the true nature of dark matter. Each theory, whether it posits dark matter as a tangible entity or as a manifestation of new physics, adds a layer of complexity to the puzzle, one that could forever alter our understanding of the cosmos. On the other hand, dark energy is an entirely different kind of mystery, one that is even more difficult to grasp due to its elusive and invisible nature. Dark energy is thought to be the force responsible for the accelerated expansion of the universe. Imagine the universe as a balloon that continuously grows larger as air is blown into it. As the balloon expands, the galaxies within it move farther apart from one another. However, recent observations have shown that this expansion is not only ongoing, but actually speeding up. This accelerated expansion is where dark energy comes into play. It acts like an invisible force that pushes galaxies apart, counteracting the gravitational pull that would otherwise draw them closer together. Unlike matter, which is tangible and interacts with light, dark energy has no direct interaction with the electromagnetic spectrum, making it invisible to our detection methods. Its very nature is something that defies our everyday understanding of the universe. Yet, despite its unseen presence, dark energy seems to make up approximately 68% of the total energy content of the universe. This astonishing figure was first inferred in the late 20th century through the study of distant supernovae, massive explosions of dying stars. These supernovae appeared dimmer than expected, indicating that they were farther away than previously thought. This observation pointed to the fact that the universe's expansion was accelerating, not slowing down as had been assumed. So, what does dark energy actually do? In essence, it acts as a repulsive force, pushing galaxies away from one another. It is a force that opposes the pull of gravity, which naturally works to bring matter together. As a result, while gravity pulls galaxies toward one another, dark energy stretches the very fabric of space itself, causing everything in the universe to move apart at an ever-increasing rate. This phenomenon has far-reaching consequences for the future of the universe, as scientists strive to understand whether dark energy is a constant force throughout space, or if it is a dynamic, ever-changing field that evolves as the universe itself evolves. In the quest to unravel the true nature of dark energy, scientists use a combination of observational techniques and theoretical models. By studying the movement of galaxies and how quickly they are drifting apart, they are able to gather vital data about the rate at which the universe is expanding. One of the primary methods for studying dark energy involves examining the light emitted by distant supernovae. The dimming of this light offers clues about the expansion rate of the universe and helps researchers gauge the presence of dark energy. In addition to this, scientists employ a range of telescopes that detect light across different wavelengths, from visible light to infrared radiation and beyond. These observations provide detailed insights into the distribution of matter and the interactions between dark energy and the visible components of the universe. Theoretical physicists have proposed several hypotheses to explain dark energy's nature. One such theory posits that dark energy is a constant energy density that permeates all of space. This concept is often linked with the idea of vacuum energy, which suggests that even in the emptiness of space, fluctuations in energy contribute to the universe's accelerated expansion. Another possibility is that dark energy is not constant but evolves over time, a notion captured by the theory of quintessence. In this model, the energy density of dark energy varies as the universe ages, leading to changes in its influence on the cosmos. There are also theories that suggest modifications to our understanding of gravity, proposing that dark energy could be the result of altered gravitational laws on cosmic scales. Despite the numerous hypotheses, no one theory has emerged as the definitive explanation for dark energy. However, with each new discovery and technological advance, scientists are getting closer to understanding this mysterious force. The implications of dark energy are far-reaching, shaping not only the expansion of the universe, but also its future. If dark energy continues to dominate, it could lead to a scenario known as the Big Freeze, where galaxies drift apart and the universe becomes an ever-expanding, cold, and dark void. On the other hand, if dark matter's gravitational influence grows stronger than dark energy's repulsive force, the universe may eventually slow its expansion and collapse in a big crunch, where all matter is drawn back together. Both dark matter and dark energy are fundamental to the structure of the universe. Dark matter acts as the unseen glue that holds galaxies together, providing the necessary gravitational pull to prevent stars and gas from flying apart as they move through space. Although it does not emit, absorb, or reflect light, dark matter reveals its presence through its gravitational effects on visible matter. Imagine a galaxy spinning like a pinwheel. Dark matter is the invisible force keeping everything in place. ensuring that the galaxy maintains its shape and structure. Without dark matter, galaxies would not form as we observe them today, and the universe would lack the intricate structures we see in the cosmos. Conversely, dark energy plays an opposing role, accelerating the expansion of the universe. While gravity pulls matter together, dark energy pushes it apart, leading to an ever-expanding universe. The ultimate fate of the universe hinges on the delicate balance between these two cosmic forces. If dark energy continues to accelerate the expansion, the universe may drift toward an isolated future, where galaxies are increasingly separated. Alternatively, if dark matter's gravitational pull outweighs dark energy's repulsive force, the expansion could slow down and potentially reverse, leading to a cosmic collapse. In the grand scheme of the universe, dark matter and dark energy are not just fascinating curiosities. They are the key players in determining the future of everything within the cosmos. Their interaction shapes the formation and evolution of galaxies, the distribution of matter, and the ultimate destiny of the universe. Understanding these forces is critical for unlocking the mysteries of the universe's past and its future. One of the most captivating phenomena in the universe is the neutron star, an exotic remnant of a massive star's explosive death. When a star has exhausted its nuclear fuel, it can no longer support itself against the crushing force of gravity. The outer layers of the star are expelled in a violent supernova, leaving behind a dense core that collapses under immense pressure. This core, which consists primarily of neutrons, is one of the densest objects in the universe, with a mass greater than the Sun but a size no larger than a city. The density of a neutron star is so extreme that a single cubic centimeter of its material would weigh as much as a mountain here on Earth. Neutron stars also exhibit fascinating properties due to their small size and immense mass. Their gravitational field is so intense that it warps space-time, causing time to pass more slowly near the star than it does farther away. This extreme gravity also leads to some neutron stars spinning at incredible speeds, completing a full rotation several times per second. These rapidly rotating stars can emit beams of radiation from their magnetic poles, creating a lighthouse effect that allows scientists to detect periodic pulses of light as the beams sweep across the sky. In conclusion, the study of dark matter, dark energy, and neutron stars offers a tantalizing glimpse into the unknown forces that govern the universe. Through the lens of scientific inquiry and exploration, we continue to push the boundaries of our understanding, seeking to unlock the secrets that lie at the heart of the cosmos. With every discovery, we move one step closer to understanding the true nature of the universe, our place within it. The magnetic field of a neutron star is an extraordinary phenomenon, one so remarkably powerful that it surpasses anything we could ever imagine on Earth. These magnetic fields, many times stronger than those produced by any terrestrial magnet, can exert profound effects on their surroundings. The intensity of these fields is so extreme that they have the potential to influence surrounding matter in ways that we are still trying to fully understand. In fact, they can even trigger the emission of high-energy radiation, including X-rays, which provide valuable insights into the nature of these celestial objects. The magnetic forces at play around a neutron star are not just curious anomalies. They are a key feature in a cosmic landscape that challenges everything we think we know about the universe. Neutron stars themselves are the remnants of massive stars that have undergone a violent and transformative collapse at the end of their life cycles. These stellar remnants are not just incredibly dense, but they also exhibit rapid rotation and powerful magnetic fields that make them unlike any other object in the universe. In fact, neutron stars stand as one of the most fascinating and mysterious outcomes of stellar evolution. They offer a glimpse into extreme conditions that go far beyond what we can replicate here on Earth, opening up new windows into the fundamental laws of physics. These objects serve as living laboratories for scientists to test theories about gravity, electromagnetism, and quantum mechanics under conditions that no earthly experiment could ever replicate. Among these celestial oddities, pulsars stand out. A pulsar is a neutron star that emits beams of electromagnetic radiation from its poles. As it spins, these beams sweep across the sky like the rotating light of a lighthouse. The rhythmic pulsations we detect from Earth are the result of these beams crossing our line of sight, much like a lighthouse beam that shines out over the ocean, illuminating the vast expanse around it. Pulsars act as cosmic beacons, sending out signals that can be detected from great distances, serving as one of the most intriguing objects in the universe. Imagine a universe teeming with secrets, vast and unfathomable, where every star and shadow holds a story waiting to be discovered. Our journey through space takes us to some of the most perplexing and awe-inspiring phenomena ever observed, phenomena that stretch our imagination and challenge the limits of human knowledge. From the impenetrable realms of black holes, colossal giants that consume everything in their vicinity, to the elusive forces of dark matter and dark energy, which influence the cosmos in ways we cannot see or fully comprehend, the universe continues to keep us on the edge of discovery. As we venture into the unknown, we will encounter neutron stars that spin at incredible speeds, quasars that radiate energy more powerful than entire galaxies, and exoplanets that orbit distant stars in faraway systems. These objects, as enigmatic as they are, offer a window into the fundamental forces shaping the cosmos. The study of these mysterious objects is not just an academic pursuit. It is a journey of exploration, pushing the boundaries of human understanding and shedding light on the most obscure corners of the universe. Our fascination with the universe is not just about seeking answers. It is rooted in the human instinct to explore, to seek meaning, and to understand our place in the cosmos. From the earliest times, people have looked up at the stars and wondered what lies beyond our small blue planet. This desire to know the unknown is not a modern development. It has been a part of human nature for millennia. Ancient civilizations such as the Babylonians and Egyptians built their lives around the cycles of the moon and the stars. These celestial movements were not only important for agricultural purposes, but were also woven deeply into religious practices and beliefs, creating a rich tapestry of mythology and astronomy that laid the foundation for the scientific exploration of the skies. As time progressed, our understanding of the universe deepened. Greek philosophers like Aristotle offered early musings on the cosmos, setting the stage for centuries of thought. But it wasn't until the work of astronomers like Copernicus and Galileo that our perspective truly shifted. Copernicus's heliocentric model, which proposed that the Earth orbits the Sun, challenged the long-held geocentric view and sparked a profound shift in our understanding of the universe. This was not just a scientific revolution. It was a cultural upheaval, as it questioned the very structure of reality itself. This shift in thought sparked an intellectual renaissance, leading to the scientific revolution, where new ideas and discoveries began to reshape society in profound ways. Galileo's observations through the newly invented telescope were groundbreaking. He discovered moons orbiting Jupiter, which directly contradicted the ancient belief in a perfectly ordered, unchanging universe. Instead, he revealed a chaotic and unpredictable cosmos, filled with complex phenomena that challenged our understanding of nature. This realization that the universe was far more dynamic and unpredictable than previously thought spurred an era of scientific discovery, where every new observation, whether it was the rings of Saturn or the moons of Jupiter, drove humanity to seek further answers. In modern times, the study of the most mysterious objects in the universe, such as black holes, dark matter, and neutron stars, continues to push the boundaries of scientific inquiry. These objects are not just fascinating for their ability to capture our imagination. They also present challenges that require new theories, new tools, and new ways of thinking. To explore the mysteries of the universe, we have developed increasingly sophisticated instruments, such as space telescopes, particle accelerators, and observatories, that allow us to peer deeper into the cosmos than ever before. These tools are a testament to human ingenuity, our ability to create the means to explore the unknown, and our relentless pursuit of understanding. The desire to explore the universe, to uncover its mysteries, and to push the limits of knowledge is at the heart of space exploration. It embodies the resilience and ingenuity of humanity, inspiring people around the world to dream of a future where we can travel beyond our home planet, discover new worlds, and ultimately understand our place in the vastness of the cosmos. This journey, fueled by curiosity and an insatiable drive to learn, is more than just an intellectual pursuit. It is a testament to our collective determination to reach for the stars and beyond. Every time we gaze up at the night sky, we are reminded that there is still so much to uncover. And in that pursuit of knowledge, we find purpose, excitement, and the promise of discovery. The pursuit of knowledge, particularly in the realm of astrophysics and cosmology, is a force that shapes not only scientific understanding, but also the very fabric of human culture and philosophy. It transcends borders, fostering collaboration among scientists from diverse disciplines and regions. As researchers and scholars unite in their common goal to understand the universe, their collective efforts transcend differences, enabling a global conversation that spans both time and space. This collaborative spirit, shared by nations, institutions, and individuals alike, speaks to our collective human curiosity, a shared yearning to understand the mysteries of existence and the cosmos. In our pursuit to unlock the universe's most profound secrets, we also find ourselves reflecting on our place within this vast expanse. What is our role in this grand cosmic theater? Are we simply an insignificant blip in the infinite void, or are we part of a larger, interconnected narrative that shapes our world? This quest for knowledge, as it unravels the deepest mysteries of existence, also invites a sense of unity among us. It encourages humanity to see itself as a part of something much greater, a cosmic web in which all things are interwoven. This shared sense of purpose, this deep, innate curiosity, has not only redefined the trajectory of human history, but also driven monumental advancements in technology, science, and philosophy. It fuels our collective imagination, urging future generations to look up at the stars, pushing the boundaries of what we know. The mysteries of the universe are endless, and one of the most captivating among them is the phenomenon known as black holes. These cosmic entities defy our understanding of the natural world. They are regions in space where the gravitational pull is so powerful that nothing at all can escape their grasp. Not even light, which travels at the fastest speed known to physics, can break free. The sheer enigma of black holes makes them one of the most perplexing objects in the universe. Because black holes do not emit any light, they cannot be seen directly. Instead, astronomers observe their effects on the surrounding space, such as the way they distort the motion of nearby stars or pull in surrounding gas. Then there are neutron stars, born from the violent explosion of a massive star in a supernova. When a star reaches the end of its life, its core can collapse, leading to the formation of a neutron star. These stellar remnants are incredibly dense. Just a teaspoon of neutron star material would weigh as much as an entire mountain on Earth. Some neutron stars spin at extraordinary speeds, generating immense magnetic fields, and certain neutron stars emit beams of radiation that sweep across the cosmos in regular pulses, like a lighthouse shining through the dark vastness of space. These pulsars, as they are known, offer unique insights into the nature of space and time. Equally mysterious is dark matter, an invisible force that constitutes a significant portion of the universe's mass. Though dark matter cannot be directly observed, its presence is inferred through its gravitational influence on galaxies. It affects how galaxies move, interact, and cluster together. This unseen entity is one of the greatest unknowns in astrophysics, leading scientists to wonder, what is dark matter and how does it shape the cosmos? Another fascinating cosmic object is the quasar, a powerful and energetic center of distant galaxies, thought to be powered by a supermassive black hole. These quasars can outshine all the stars in their host galaxy combined, providing a beacon of light that reaches us from the farthest reaches of the universe. By studying quasars, scientists are able to peer back in time, offering a glimpse into the conditions of the early universe, long before the first galaxies and stars began to form. The search for extraterrestrial life remains one of humanity's most profound quests. The discovery of habitable planets outside our solar system forces us to confront one of the oldest and most fundamental questions. Are we alone in the cosmos? This question not only captures the imagination, but also reshapes our understanding of life itself. The possibility of life beyond Earth opens up new avenues for exploration and encourages us to consider the nature of existence in ways we never have before. As we continue to discover new exoplanets, we are reminded that our understanding of the universe is still in its infancy. There is so much left to learn, so much left to discover. Now, focusing on black holes, let's delve deeper into how they are formed. Black holes are the ultimate result of stellar evolution. When a massive star runs out of fuel, it can no longer maintain the delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity. In a cataclysmic explosion known as a supernova, the outer layers of the star are expelled, while the core collapses inward under its own immense gravitational pull. If the remaining core is massive enough, this collapse continues until the space around it is compressed so tightly that not even light can escape. This is where a black hole is born. There are various types of black holes, each with its own unique formation process and mass characteristics. The first, and perhaps most well known, are stellar black holes. These form from the remnants of individual stars and typically have a mass several times greater than that of our Sun. Then there are supermassive black holes, which reside at the centers of galaxies, including our own Milky Way. These giants contain millions to billions of times the mass of our Sun. Their origins remain a mystery, though some theories suggest that supermassive black holes could have formed from the merging of smaller black holes or the collapse of giant gas clouds in the early universe. The third category is intermediate black holes. These are somewhat elusive and difficult to detect, but they likely form in dense star clusters. Scientists are still working to fully understand their role in the cosmic puzzle. Black holes also present a challenge to our understanding of space and time. The event horizon, which is the boundary beyond which nothing can escape, acts as a one-way threshold. It's as if you are at the edge of an immense well. Once light or matter crosses this threshold, there is no way back. The gravitational pull at the event horizon is so intense that it warps the very fabric of space itself. For light, this is particularly significant. Light, which travels at the fastest speed possible in the universe, is forced to give up its speed and fall into the black hole's core. This warping of space-time near black holes leads to some fascinating effects. Time itself is not experienced the same way inside a black hole as it is elsewhere in the universe. The intense gravitational field causes time to slow down as one approaches the event horizon. From the perspective of someone far from the black hole, time appears to stand still for anything crossing the event horizon. However, for the object falling in, time continues normally, creating an intriguing paradox. These effects are not just theoretical, they have been confirmed through indirect observations, such as the way the light from stars and gas behaves as it is pulled into a black hole's vicinity. The discovery of gravitational waves, ripples in the fabric of spacetime caused by the collision of massive objects, is another breakthrough that has revolutionized our understanding of the universe. These waves, which were first detected in 2015, offer a completely new way of listening to the cosmos. When two black holes spiral toward each other and merge, they create these waves, which carry vital information about their origins. Gravitational waves allow scientists to observe phenomena that are invisible to traditional telescopes. For example, the merging of two black holes provides insight into their mass, spin, and the dynamics of their collision. Each detection of gravitational waves helps us piece together the cosmic puzzle, revealing hidden details about the behavior and distribution of black holes across the universe. In this never-ending quest to explore the unknown, our pursuit of understanding not only shapes the future of science, but also influences the course of human history. The more we discover about black holes, neutron stars, dark matter, quasars, and the possibility of extraterrestrial life, the more we realize just how much is still left to uncover. Every answer leads to new questions, and this cycle of curiosity continues to drive humanity's greatest achievements, urging us to look toward the stars and imagine what lies beyond. Furthermore, this groundbreaking discovery heralds the dawn of a new era in astrophysics, one that promises to transform our understanding of the cosmos in ways once thought impossible. This era is called multi-messenger astronomy, an approach that merges different types of observations, including gravitational waves, electromagnetic radiation, and particles emitted from cosmic events. Through this revolutionary method, scientists can delve much deeper into the mysteries of the universe, unlocking secrets that have remained hidden for eons. By combining these various forms of cosmic signals, researchers can piece together a more complete and multifaceted understanding of the universe's most extreme environments. This multifaceted approach allows scientists to probe the cosmos in ways that were once unimaginable, enabling them to uncover phenomena that are both violent and enigmatic, shaping the very fabric of the universe. It is not simply a technical achievement, but rather a monumental step towards unraveling the intricate and complex tapestry of space-time. For the first time, the universe's most elusive processes, the ones that govern everything from star formation to the birth and death of galaxies, are within our reach, offering unprecedented opportunities for discovery. One of the most profound breakthroughs in recent years has been the detection of gravitational waves, ripples in space-time caused by cataclysmic events such as the collision of two black holes. These waves, though invisible to the naked eye, travel across the universe, carrying with them invaluable information about the properties of the objects that cause them. Specialized detectors on Earth, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, have now successfully detected these ripples, marking an extraordinary achievement in modern physics. The study of gravitational waves opens up an entirely new avenue for exploring the universe, offering glimpses into the violent processes that shape the cosmos and the fundamental laws of nature. In the realm of black holes, those enigmatic regions of space where gravity is so strong that nothing, not even light, can escape, scientists have developed innovative methods to observe and study these invisible giants. Despite their lack of visible light, black holes exert tremendous gravitational forces that can be detected in various ways. One of the primary methods involves observing the effects of a black hole's immense gravity on nearby stars and gas. As a black hole pulls in matter from a neighboring star, this material forms a swirling accretion disk around the black hole. The intense gravitational forces at play cause the gas and dust in the disk to heat up to extreme temperatures, producing powerful X-ray radiation. Telescopes on Earth can capture this radiation, providing a glimpse into the otherwise hidden regions of space. Additionally, astronomers often track the movements of stars that orbit invisible objects. When a star is seen orbiting a point in space where no visible object exists, it strongly suggests that a black hole is present. By studying the star's motion, particularly how quickly it moves, scientists can infer the mass and presence of the black hole, offering vital clues about its size and properties. This indirect method of detection is one of the most powerful tools for uncovering the existence of black holes in the universe. A particularly exciting development in black hole research involves the detection of gravitational waves caused by the collision of two black holes. When two of these colossal objects spiral toward each other and merge, they release an enormous amount of energy in the form of gravitational waves. These waves travel across the universe and can be detected by sensitive instruments on Earth, offering insight into the nature of the black holes involved in the merger. This not only deepens our understanding of black holes, but also helps to confirm some of the most fundamental predictions of Einstein's theory of general relativity. Looking to the future, the ultimate goal of black hole research is to capture direct images of these mysterious objects. The Event Horizon Telescope, EHT, for example, has already succeeded in capturing the shadow of a supermassive black hole at the center of the galaxy M87. By observing the way in which the black hole's immense gravitational pull bends light around it, scientists can create a visual representation of the black hole's event horizon, the boundary beyond which nothing can escape. This marks a monumental leap in our ability to study black holes, allowing us to observe them not just indirectly, but directly. Black holes play a crucial role in the evolution of galaxies, influencing their formation and growth in ways that scientists are still striving to fully understand. At the center of many galaxies, including our own Milky Way, lies a supermassive black hole, one that can contain millions or even billions of times the mass of our Sun. These supermassive black holes are not passive objects. They are active agents that profoundly influence the stars, gas, and dust that surround them. One of the key ways they do this is through their immense gravitational pull. A supermassive black hole's gravity affects the motion of stars and gas clouds within the galaxy, shaping the overall dynamics of the galaxy's structure. As material from the surrounding galaxy spirals toward a black hole, it forms an accretion disk. A swirling structure can reach incredibly high temperatures. This disk can emit massive amounts of energy, sometimes outshining entire galaxies. This phenomenon offers scientists a rare opportunity to study black holes and their interactions with their environment, shedding light on the otherwise hidden forces at play within these cosmic behemoths. Moreover, black holes play an essential role in regulating star formation within galaxies. When a black hole consumes a significant amount of material, it can release vast amounts of energy in the form of powerful jets or winds. These energetic outflows can push away surrounding gas, preventing it from collapsing into new stars. This process helps to slow down star formation, ensuring that galaxies do not become overly dense with stars too quickly. This feedback mechanism plays a crucial role in balancing the growth of galaxies over billions of years. When galaxies collide, a common event in the dynamic cosmos, the black holes at their centers can also interact with one another. As the two galaxies merge, their central black holes may draw closer together, eventually merging into an even larger black hole. This merging process has a significant impact on the galaxy, redistributing energy and material in ways that can alter its dynamics and structure. The merging of black holes is one of the most dramatic and energetic events in the universe, helping to shape the very evolution of the galaxies involved. The role of black holes in a galaxy's life cycle is pivotal, as they act as engines that drive cosmic change. They influence the rate of star formation, the arrangement of stars and gas, and ultimately the fate of the galaxy itself. Understanding these intricate roles helps to highlight how black holes are intertwined with the fundamental processes of cosmic evolution, acting as both the destroyers and creators of galactic structures. Dark matter, another mysterious substance that makes up a significant portion of the universe's mass, is equally elusive. Though invisible and undetectable by conventional means, its presence is inferred through its gravitational effects on visible matter, such as stars and galaxies. Imagine standing in a vast stadium, watching a game where you can only see the players on the field. The crowd, though invisible, still influences the movement and actions of the players. Similarly, dark matter, though we cannot see it directly, exerts a profound influence on the behavior of the visible matter around it. The concept of dark matter was first proposed in the early 20th century by astronomer Fritz Zwicky, who was studying the Coma Cluster, a massive collection of galaxies. Zwicky noticed something strange. The galaxies in this cluster were moving so rapidly that according to the laws of physics, they should have flown apart. However, they were not. Zwicky hypothesized that there must be some unseen mass exerting gravitational influence on the galaxies, holding them together. This was one of the earliest indications of dark matter's existence. Subsequent observations and studies have provided further evidence of dark matter's presence. For example, scientists have observed that stars at the outer edges of galaxies are rotating much faster than expected, based solely on the visible mass of the galaxy. This suggests that these stars are being affected by an invisible source of mass, dark matter, that we cannot see but can detect through its gravitational effects. Today, dark matter is considered a fundamental component of the universe, making up roughly 25% of its total mass. While it may seem like a large portion, it remains one of the greatest mysteries of modern astrophysics. Unlike ordinary matter, such as the stars, planets, and galaxies that we can observe, dark matter does not emit light or any form of radiation. As a result, it remains invisible, detectable only by its gravitational influence on the visible matter around it. The majority of dark matter is thought to reside in and around galaxies. If you imagine a galaxy as a spinning disk of stars and gas, the majority of its mass, its invisible halo, exists beyond what we can directly observe. This unseen mass helps to hold galaxies together and influences their rotation. The speed at which stars move within a galaxy suggests that there is far more mass present than we can account for through visible matter alone. This gravitational influence provides strong evidence for the existence of dark matter, and its vital role in shaping the structure of the universe. Dark matter, although invisible, plays an indispensable role in shaping the universe as we know it. Far from being confined to individual galaxies, dark matter clusters on a much larger scale, forming vast, interconnected structures known as galaxy clusters. These massive, gravitationally bound groups of galaxies rely on dark matter to maintain their cohesion. Without it, the galaxies within them would be scattered across the cosmos, unable to stay bound together. Through its unseen gravitational pull, dark matter directs the formation and motion of countless galaxies, influencing their paths and interactions in ways that continue to intrigue and confound scientists. This invisible force fundamentally alters our perception of the universe. It suggests that the universe we see and can study with our most advanced telescopes is only a fraction of the true cosmic picture. In fact, dark matter hints at a much deeper and more intricate web of forces and structures, extending far beyond our current observational reach. It operates in the shadows, impacting the formation and dynamics of everything from star systems to entire galaxies, making it one of the greatest enigmas in modern astrophysics. Despite the countless advances in technology, understanding dark matter remains one of the most profound challenges of contemporary science. As it stands, dark matter accounts for a significant portion of the universe's total mass, though it is entirely undetectable through conventional means. This unseen substance does not emit, absorb, or reflect light, rendering it completely invisible to our most sophisticated telescopes. Its existence is inferred only through its gravitational effects on visible matter. Scientists have put forward a variety of theories to explain what dark matter might actually be, each offering a unique perspective on its elusive and enigmatic nature. One of the leading theories proposes that dark matter is composed of weakly interacting massive particles, commonly referred to as WIMPs. These hypothetical particles are predicted to have a considerable amount of mass, far greater than that of many familiar particles, yet they interact very weakly with normal matter. This minimal interaction makes detecting them incredibly difficult, as they don't engage with light in any way. If WIMPs exist, they are believed to have been abundant in the early universe, formed during the high-energy conditions shortly after the Big Bang. Alternatively, some scientists propose that dark matter could be composed of a different class of particles known as axions. These particles are much lighter than WIMPs and are theoretically predicted by certain frameworks of physics, particularly those concerning the strong nuclear force. Axions, if they exist, could fill the universe in vast quantities, and their gravitational effects would mimic the influence of dark matter. What makes axions particularly intriguing is that they might be detectable under specific conditions, offering researchers a potential path for their study. However, proving the existence of axions remains a formidable challenge, as they would only reveal themselves in very particular scenarios. Another possibility is the existence of primordial black holes. These black holes, much smaller and less massive than the supermassive ones found at the centers of galaxies today, may have formed in the early moments of the universe, shortly after the Big Bang. Despite their small size, primordial black holes exert gravitational forces strong enough to account for the mysterious effects we attribute to dark matter. What makes them particularly interesting is that, unlike more familiar black holes, primordial black holes would not emit light, making them invisible in the traditional sense. Their presence, however, could help explain the cosmic phenomena that have long puzzled astrophysicists. In addition to these particle-based theories, some researchers are exploring the possibility that the apparent effects of dark matter could be explained by modifications to our understanding of gravity. According to certain theories, gravity might behave differently on cosmic scales, leading to effects that we interpret as the presence of dark matter. This line of thought proposes that what we observe as dark matter might in fact be a misinterpretation of gravitational forces, suggesting the need for new and innovative physics to explain the phenomena without invoking unseen particles. Each of these theories, though intriguing, remains speculative, with none yet proven by concrete evidence. As our observational techniques advance, new experiments and discoveries bring us ever closer to unraveling the true nature of dark matter. The sheer scale and influence of dark matter on the universe's structure and evolution make it an essential component in our ongoing quest to understand the cosmos. Yet, despite decades of research and observation, the answers remain tantalizingly out of reach. In parallel with the mystery of dark matter, there is another cosmic riddle that has taken center stage in the field of cosmology: dark energy. Unlike dark matter, which is invisible and exerts a gravitational pull, dark energy is believed to be the force responsible for the accelerated expansion of the universe. Imagine the universe as a balloon, continuously growing larger as you blow air into it. As the surface of the balloon expands, galaxies drift further apart from one another. However, recent observations have revealed something more perplexing. The expansion of the universe is accelerating, not slowing down as once expected. This is where dark energy comes into play. Dark energy can be thought of as an unseen force that permeates all of space. Unlike matter, which has weight and can be observed, dark energy does not interact with light, rendering it completely invisible and incredibly difficult to detect. Despite its elusive nature, dark energy seems to make up a significant portion of the universe, accounting for more than 3/4 of all the observable mass and energy in the cosmos. This discovery came about in the late 20th century when scientists were studying distant supernovae, massive stellar explosions. These supernovae appeared dimmer than expected, indicating that they were farther away than anticipated due to the accelerating expansion of the universe. So, what does dark energy do? Essentially, it acts like a repulsive force, counteracting gravity's pull and pushing galaxies further apart. While gravity tries to draw matter together, dark energy stretches the fabric of space itself, causing the acceleration of the universe's expansion. The exact nature of dark energy remains one of the most perplexing questions in modern cosmology. Its properties and the way it interacts with the rest of the universe continue to defy understanding. Researchers are striving to decode whether dark energy is a fundamental property of space, a dynamic field that evolves over time, or something altogether different. Scientists are making strides in unraveling the nature of dark energy through a combination of observation and theoretical physics. By studying the movement of galaxies and the way they drift apart, researchers can gain insight into how dark energy influences the universe's expansion. They often analyze light from distant supernova, brilliant bursts of energy produced by dying stars, since these explosions offer valuable information about the rate at which the universe is expanding. Through these observations, scientists have confirmed that the universe is indeed expanding at an accelerating rate, providing indirect evidence for the presence of dark energy. To study dark energy further, astronomers use advanced telescopes that detect light across various wavelengths, from visible light to infrared and beyond. These observations help them gather crucial data about galaxies and other cosmic structures. Through these investigations, researchers have sometimes noticed patterns in how matter is distributed throughout space, hinting at the potential interactions between dark energy and ordinary matter. Several theories about the nature of dark energy continue to emerge. One hypothesis is that dark energy represents a constant energy density that permeates all of space, often referred to as vacuum energy. This concept suggests that even in the emptiest regions of space, there may still be tiny fluctuations of energy that contribute to the universe's expansion. Another possibility is that dark energy changes over time, evolving in concert with the universe itself. This idea, known as quintessence, suggests that the energy density of dark energy could vary, influencing the acceleration of the universe in different ways over time. Some researchers even consider the possibility that dark energy is a manifestation of modifications to gravity itself. This theory proposes that our understanding of gravity might need to be adjusted on cosmic scales, offering alternative explanations for the observed acceleration of the universe. Each of these hypotheses opens up exciting new avenues of exploration, presenting fresh opportunities to expand our understanding of one of the universe's greatest mysteries. While much remains unknown, the study of dark energy and dark matter is crucial to understanding the universe's structure and its ultimate fate. Together, these invisible and intangible forces hold the key to comprehending the full scope of the cosmos, how it came into being, how it has evolved, and where it is headed in the future. As our observational capabilities improve and new theories emerge, the hope is that we will one day uncover the hidden forces that shape the very fabric of our universe. However, scientists have managed to detect the presence of dark matter, not directly, but by observing its profound influence on visible matter. Imagine a galaxy as a spinning pinwheel in the vast expanse of space. Now picture dark matter as the invisible force that binds it all together, holding the galaxy in place and providing the necessary gravitational pull to prevent the stars, gas, and dust from flying apart as they whirl through space at incredible speeds. Without dark matter, galaxies as we observe them today would simply not exist. The universe would be a very different place, one where clusters of stars would drift aimlessly through the cosmos, lacking any structure or cohesion. In contrast, dark energy plays an equally crucial role, but in a completely different way. It governs the expansion of the universe. Imagine the cosmos as a balloon being inflated. Initially, the expansion was driven by gravity, pulling everything together in a delicate balance. But over time, dark energy has taken over, exerting a force that drives galaxies away from each other, causing the expansion of the universe to accelerate. This force is essentially a counterbalance to gravity. While dark matter pulls everything together and forms the structure of the universe, dark energy pushes everything apart. Together, these two mysterious forces, dark matter and dark energy, create the tension that defines the future of our universe. The fate of the cosmos will depend largely on the delicate balance between these forces. If dark energy continues to dominate, it may eventually lead to a state known as the Big Freeze, where galaxies are driven further apart, leaving the universe in a cold, dark, and isolated state. Meanwhile, on a more localized scale, some of the most fascinating objects in the universe emerge from the explosive death of massive stars, neutron stars. These stellar remnants are born from a cataclysmic event known as a supernova. When a star exhausts its nuclear fuel, it no longer has the energy to fight against its own gravity, which causes the star to collapse under its immense weight. As the outer layers of the star explode outward, the core is compressed to such a degree that protons and electrons are forced to merge, forming neutrons. The result is an incredibly dense object, no larger than a city, yet containing a mass greater than the sun itself. The density of a neutron star is absolutely staggering. To put it into perspective, a single cubic centimeter of neutron star material weighs more than an entire mountain on Earth. This is because the neutrons are packed together so tightly that they defy our usual understanding of matter. Neutron stars also have an extraordinarily strong gravitational field. Their immense mass, coupled with their small size, means that the gravitational pull near them is so intense that it can warp space-time itself. Time, in fact, can appear to run slower the closer you get to a neutron star compared to farther distances. Perhaps one of the most mesmerizing features of a neutron star is its rotation. These stellar remnants spin at breathtaking speeds, completing a full rotation multiple times per second. This rapid rotation can turn the neutron star into what is known as a pulsar, an object that emits beams of radiation from its magnetic poles. As these beams sweep across space, they create a lighthouse effect. Imagine standing on a coastline, watching a lighthouse beam light up the darkness, and you can only see it when the light sweeps past. In the same way, a pulsar emits pulses of light, radio waves, visible light, or even X-rays, which we detect on Earth as periodic flashes of radiation. The magnetic field of a neutron star is also incredibly strong, far stronger than anything we encounter on Earth. This powerful field can have significant effects on nearby matter, sometimes even causing the emission of high-energy radiation, such as X-rays. These pulsars are not just fascinating astronomical objects. They are key players in the study of astrophysics, providing a window into the fundamental laws of physics under extreme conditions. A pulsar, which is a type of neutron star, stands out because it emits beams of radiation from its magnetic poles. These beams are detected as periodic pulses of light, much like the rhythmic flashes from a lighthouse. The pulsar's rapid rotation and intense magnetic field create a focused beam that sweeps across space. This sweeping effect is what leads to the pulsing signal we observe from Earth. However, not all neutron stars are pulsars. The conditions must be just right for a neutron star to emit these periodic radiation pulses. The star must have a strong magnetic field and must be rotating at an incredibly fast speed. The relationship between neutron stars and pulsars is thus very specific. While all pulsars are neutron stars, not all neutron stars become pulsars. For this transformation to occur, a particular set of criteria must be met, namely, the star's rotation and magnetic field must align in such a way that the radiation beams are emitted and detected by observers on Earth. When the conditions are right, the neutron star's rapid rotation combined with its powerful magnetic field creates a highly concentrated beam of radiation that gives rise to the distinctive pulsating signal. Neutron stars are one of the most extreme forms of matter in the universe. They serve as natural laboratories for studying the fundamental forces of nature, particularly the strong nuclear force. This force is responsible for holding atomic nuclei together, overcoming the natural repulsion between positively charged protons. Within a neutron star, gravity is so intense that it crushes atoms to such an extent that electrons and protons merge, forming neutrons. This results in a star composed almost entirely of densely packed neutrons. By studying neutron stars, scientists can gain insights into how matter behaves under conditions that are unimaginable here on Earth. The extreme density of these objects, where a single cubic centimeter of material weighs as much as a mountain, allows researchers to study the strong nuclear force in action. By observing how matter behaves under such immense pressures, astrophysicists can work out the details of particle interactions and gain clues about the fundamental laws that govern the universe. These stellar remnants are more than just objects of scientific curiosity. They hold the key to understanding the deepest mysteries of physics. Neutron stars, with their extreme density, rapid rotation, and powerful magnetic fields, offer a glimpse into the very building blocks of the cosmos. The study of neutron stars, pulsars, and the forces that shape them allows us to peer into the workings of the universe at its most extreme, bringing us closer to understanding the fundamental forces that govern everything from the tiniest particles to the largest structures in the cosmos. Neutron stars are some of the most fascinating and extreme objects in the universe, with characteristics that make them key players in our quest to understand the forces that govern the cosmos. These stellar remnants, which form when massive stars collapse under their own gravity at the end of their life cycles, are incredibly dense. A single cubic centimeter of a neutron star can weigh about 400 million tons, making them not only small in size but also immensely heavy. What makes them so intriguing is their ability to generate extremely strong gravitational fields, allowing scientists to test theories of gravity in ways that were once thought impossible. One of the most significant contributions of neutron stars to modern physics is their role in testing Einstein's theory of general relativity. When two neutron stars collide, they produce gravitational waves, ripples in the very fabric of space-time itself. These waves can be detected on Earth, even though they come from distances billions of light years away. The detection and study of these waves provide invaluable insights into the nature of gravity and the behavior of matter under the most extreme conditions imaginable. Such observations offer a glimpse into how gravity operates not only in our local environment, but also in the heart of the most intense cosmic events. Scientists have also studied neutron stars through their magnetic fields and rapid rotations, revealing how these forces interact and shape the broader cosmic environment. In essence, these tiny but mighty remnants of once giant stars illuminate fundamental aspects of the universe that remain shrouded in mystery. The unique properties of neutron stars have transformed them into essential tools for understanding the interactions between nuclear forces, gravity, and the very structure of space and time itself. The fact that they allow us to probe such extreme environments makes them indispensable in our ongoing journey to understand the laws of nature and how they function across the cosmos. The study of neutron stars reveals a delicate balance of forces, from the nuclear forces that bind atoms to the cosmic scale of gravity that governs the movements of galaxies, stars, and other celestial bodies. In a way, neutron stars serve as cosmic laboratories, offering a closer look at the intricate workings of the universe. In addition to neutron stars, another group of cosmic phenomena that provides an immense amount of knowledge about the universe are quasars. These extraordinary celestial objects are some of the brightest and most luminous entities we can observe, thanks to the supermassive black holes at the centers of their host galaxies. A quasar's light can be billions of times more powerful than the combined brightness of all the stars in an entire galaxy. At the heart of each quasar lies a supermassive black hole, whose mass can range from millions to billions of times that of our Sun. Surrounding this black hole is an accretion disk made up of gas and dust, which is being slowly drawn into the black hole by its overwhelming gravitational pull. As this material spirals inward, it is compressed and heated by intense friction and gravitational forces, reaching temperatures so high that it emits vast amounts of electromagnetic radiation, including visible light, X-rays, and radio waves. The result is a brilliant, energetic burst of radiation that can outshine entire galaxies. Quasars are typically found at great distances from Earth, often billions of light years away. Their immense brightness makes them visible even at these vast distances, and the study of these objects offers a unique window into the early universe, allowing astronomers to study the conditions that existed billions of years ago, when the universe was still in its infancy. One of the key aspects of quasars is their role in revealing the growth and evolution of galaxies. Because they were most active during the early stages of the universe, studying quasars provides vital clues about the formation of galaxies, the influence of supermassive black holes, and the dynamics of the early cosmos. Quasars act as beacons of light, revealing not only the violent processes happening near the black hole, but also the physical laws governing these extreme environments. They underscore the central role of supermassive black holes in galaxy evolution, offering a deeper understanding of the gravitational forces that shape entire galaxies. Alongside quasars, another particularly captivating type of object in the universe is the blazar. A blazar is a specific type of active galactic nucleus, AGN, that emits extraordinary amounts of energy and radiation, with one key distinction: the direction of its powerful jets. These jets are narrow streams of charged particles that are expelled at nearly the speed of light from the vicinity of a supermassive black hole. When these jets are aligned with the Earth, the energy we observe is highly concentrated, resulting in intense radiation across a broad range of wavelengths, from radio waves to gamma rays. Blazars are unique not only because of their powerful jets, but also because of their variability. The energy emitted by a blazar can fluctuate dramatically on timescales as short as hours or days. This variability is caused by relativistic effects, as the particles in the jets are moving at velocities approaching the speed of light. These extreme fluctuations make blazars one of the most dynamic and energetic objects in the universe, providing a rich field of study for astronomers looking to understand the behavior of supermassive black holes and the physics behind the jets they produce. Moreover, the study of blazars contributes significantly to our understanding of active galactic nuclei and the complex processes taking place at the centers of galaxies. As with quasars, blazars also offer valuable insights into the early universe, helping astronomers piece together the evolutionary history of galaxies and their central black holes. By studying the radiation emitted by blazars, scientists can learn more about the high-energy processes that dominate the universe's most extreme environments. The search for exoplanets, or planets that orbit stars outside our solar system, has also yielded fascinating discoveries that challenge our understanding of planetary formation and the potential for life beyond Earth. Several methods have been developed to detect these distant worlds, with the transit method being one of the most common. This method involves observing the slight dimming of a star's light as a planet passes in front of it, blocking some of the star's radiation. By measuring the amount of dimming, astronomers can infer the planet's size and orbital characteristics. Another method used to detect exoplanets is known as radial velocity, which takes advantage of the Doppler effect. As a planet orbits its star, it exerts a gravitational pull that causes the star to move slightly toward and away from us. This motion causes shifts in the star's light spectrum, allowing scientists to detect the presence of a planet and estimate its mass. In some cases, advanced imaging techniques are used to directly capture the light from exoplanets, particularly those that are large and located far from their parent stars. Thanks to missions like NASA's Kepler Space Telescope, thousands of exoplanets have been discovered, including several that lie in their star's habitable zone, an area where temperatures could allow liquid water to exist. One of the most exciting discoveries is the identification of an Earth-sized planet in the closest star system to our own, raising the possibility of life beyond Earth. Other exoplanets challenge our expectations with their extreme conditions, such as gas giants orbiting incredibly close to their stars, where temperatures reach unbearable extremes. Some exoplanets are especially intriguing due to their unusual atmospheres or compositions. For example, super-Earths, which are planets larger than Earth but smaller than gas giants, may have entirely different environments from our home planet. Some have atmospheres rich in water vapor or other strange elements, hinting at chemical processes that occur under conditions that are completely alien to us. The discovery of hot Jupiters, massive gas giants that orbit very close to their stars, raises important questions about how such planets formed and why they are so different from those in our solar system. The study of exoplanets also includes examining their atmospheres. By analyzing how light passes through a planet's atmosphere during a transit, scientists can detect the presence of various chemicals, which provides valuable clues about the planet's environment. Some exoplanets exhibit unusual atmospheric phenomena, such as extreme temperature fluctuations or odd weather patterns, making them exciting subjects for ongoing research and adding to the growing body of knowledge about the incredible diversity of worlds that exist beyond our own solar system. These discoveries continue to expand our understanding of planetary systems, fueling our curiosity about the potential for life elsewhere in the universe, and challenging us to rethink what is possible when it comes to the formation of planets and the conditions required for life to thrive. The study of exoplanets not only offers the promise of discovering new worlds, but also brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? The discovery of exoplanets has been nothing short of groundbreaking, forever changing the way we perceive the universe and its vast potential. These newly identified worlds, ranging from rocky planets that could resemble Earth to gas giants with characteristics that defy our conventional understanding, offer a tantalizing glimpse into the infinite possibilities that the cosmos holds. With each exoplanet found, scientists are confronted with anomalies and surprises that challenge our current models of planetary formation and evolution, demanding a rethinking of the processes that shape planets, stars, and the systems they form. The sheer number of exoplanets discovered, each with its unique attributes, opens up new avenues for exploration, not just of these distant worlds, but also of the fundamental principles that govern the formation of planets across the universe. Some of these discoveries are so radical, so different from what we observe in our solar system, that they force scientists to reconsider the very laws of physics and gravity that we have long taken for granted. Historically, planetary formation was thought to follow a relatively straightforward process. Small particles would slowly come together, gradually building up larger bodies that would eventually become planets. This process, known as accretion, was believed to take place in a calm, predictable environment, where the interactions between particles and gravity were relatively stable. But as exoplanet discoveries increased, it became clear that this simple model was insufficient to explain the range of planetary systems we were observing. One of the most striking revelations came from the discovery of hot Jupiters, gas giants that orbit their parent stars at incredibly close distances. These planets, often many times larger than Jupiter itself, exist in regions of space where no planet in our solar system could survive. In fact, they reside so close to their stars that they have surface temperatures that can reach thousands of degrees. The presence of these hot Jupiters suggests that planetary migration, the movement of planets from their original positions to radically different locations, plays a crucial role in shaping planetary systems. Rather than forming where they are currently located, these planets may have originally formed farther from their stars and, over time, migrated inward, likely through gravitational interactions with other planets or with the surrounding protoplanetary disk. This idea challenges the traditional notion that planets are born in situ in their current orbits. Instead, the formation process may involve a far more dynamic and complex set of interactions, where planets can be moved, shifted, and influenced by the gravitational forces of neighboring bodies. These findings have not only forced a reevaluation of planetary migration, but have also shed light on the role of gravitational interactions in shaping planetary orbits and the characteristics of entire exoplanetary systems. Moreover, the diversity of planetary systems discovered adds further complexity to our understanding. Some systems contain a fascinating mix of planets, ranging from rocky worlds similar to Earth to massive gas giants, located in close proximity to one another. In our solar system, such diversity is rare, as the inner planets are mostly rocky and small, while the gas giants are situated far from the Sun. However, exoplanetary systems often feature planets of dramatically different compositions and sizes coexisting in close quarters. This raises profound questions about the conditions required for such diversity to emerge, and what environmental factors influence planetary formation on such a grand scale. Additionally, many exoplanets exhibit elliptical orbits, paths that are stretched out rather than perfectly circular. These eccentric orbits suggest that the formation and evolution of these planets are not dictated by simple accretion processes. Rather, gravitational forces from other planets, or even the host star itself, can alter a planet's trajectory over time, pulling it into new, highly eccentric orbits. This dynamic, unpredictable nature of planetary movement paints a picture of planetary systems as fluid and ever-changing, where the influence of a variety of forces can lead to unexpected results. All of these discoveries are forcing scientists to reconsider the simplicity of earlier models of planetary formation. They are now faced with the need to account for a greater range of possibilities, an expanding set of initial conditions, diverse interactions, and evolutionary paths that can lead to the creation of planets. Each new discovery, from the most bizarre exoplanetary system to the simplest rocky world, provides another piece of the puzzle, offering new insights into how planets, stars, and galaxies form and evolve over the course of billions of years. Similarly, our understanding of the universe itself continues to evolve, thanks in part to the cosmic microwave background, CMB, the faint radiation that permeates the entire universe and offers a snapshot of the cosmos from its earliest stages. The CMB is not just an afterglow of the Big Bang, but a crucial piece of evidence that provides insights into the conditions that existed when the universe was just a fraction of a second old. Imagine, if you will, the universe as a young child just waking up from a cold night. The CMB represents the afterglow of the Big Bang, radiating faintly across all of space and offering clues to its earliest moments. This radiation, which emerged about 380,000 years after the Big Bang, was the product of a universe that had cooled enough for atoms to form. Prior to this, the universe was too hot and dense for light to travel freely. But as the universe expanded and cooled, photons, or light particles, were able to move freely, marking a critical moment in the history of the cosmos. From this point onward, the universe became transparent, and the CMB became a relic of its infancy, carrying with it information about its composition, density, temperature fluctuations, and expansion. The study of the CMB has provided invaluable insights into the universe's early conditions, allowing scientists to trace the origin of galaxies, clusters, and large-scale structures. Tiny temperature fluctuations within the CMB reveal areas where matter was slightly denser, giving rise to the seeds of galaxies and other cosmic structures. These minute variations hold the key to understanding how matter clumped together over time, eventually leading to the universe we observe today. Moreover, the CMB has provided strong evidence supporting the Big Bang theory, the widely accepted explanation for the universe's origin. The patterns in the CMB suggest that the universe has been expanding ever since that initial explosive event. This evidence also supports the idea of cosmic inflation, a period of rapid expansion that occurred within the first moments after the Big Bang, providing crucial information about the universe's early growth. The CMB not only offers a window into the past, but also holds vital clues about the present and future of the universe. Its study has deepened our understanding of dark matter and dark energy, the mysterious forces that make up the majority of the universe's mass and energy. Though much remains unknown about these enigmatic components, the CMB offers an essential bridge between the universe's infancy and the present day, revealing the profound story of the cosmos in its simplest yet most profound form. In sum, the discovery of exoplanets and the study of the cosmic microwave background together represent two of the most exciting frontiers in modern science. As we continue to explore the vastness of space and examine the faint remnants of the universe's earliest moments, we are not just learning more about distant stars and planets. We are unraveling the very story of existence itself, one discovery at a time. The cosmic microwave background, CMB, serves as a profound window into the early universe, offering invaluable insights into its shape and evolution. Through its careful analysis, scientists are able to map the overall geometry of the cosmos, determining whether it is flat, open, or closed. This fundamental understanding is essential in predicting the universe's ultimate fate. Will it continue to expand endlessly? Will it gradually slow down, or could it even reverse course, collapsing into a contraction? The CMB is not merely a remnant of the past. It functions as a crucial tool in deciphering the grand narrative of the universe, its birth, growth, and potential future. It acts as a kind of cosmic time capsule, holding the faint echoes of the universe's earliest moments, thereby unlocking the secrets of its origin, its evolution, and the forces that govern its ongoing destiny. This ancient glow left behind from the Big Bang is one of the most significant discoveries in modern cosmology. The CMB is essentially a snapshot of the universe when it was just about 380,000 years old, a time when the cosmos was in a much different state, hot and dense, before cooling down and expanding into the vast, structured cosmos we observe today. Yet, despite its invaluable role in helping us understand our cosmic roots, it still carries with it a host of mysteries that keep scientists on the edge of their seats. One of the most captivating features of the CMB is its remarkable uniformity. When we look across the sky, the radiation appears almost perfectly smooth, with temperatures barely fluctuating. However, upon closer inspection, subtle variations known as anisotropies become evident. These irregularities are incredibly important because they mark the earliest stages of structure formation in the universe, suggesting the seeds of galaxies, clusters, and superclusters. But how did such structures emerge in a seemingly smooth backdrop? The answer to this question could unlock crucial information about the forces at play in the infancy of the universe. Even more intriguing is the polarization of the CMB. This polarization acts as a kind of fingerprint from the very earliest moments of the cosmos, revealing conditions that could eventually lead to the formation of galaxies. Scientists are meticulously studying these polarization patterns, looking for traces of gravitational waves, ripples in space-time caused by massive cosmic events. These gravitational waves could offer a glimpse into the mysterious phenomenon known as cosmic inflation, a period of rapid, exponential expansion that occurred within fractions of a second after the Big Bang. If these waves can be detected, they would provide direct evidence of inflation and potentially reshape our understanding of how the universe evolved in its earliest moments. Yet, detecting these faint signals remains an ongoing challenge, and the search for evidence continues to push the boundaries of our observational capabilities. The puzzle becomes even more complex with the discovery of dark matter and dark energy. These enigmatic entities comprise the vast majority of the universe's content, but their true nature remains elusive. The CMB offers critical clues about the distribution and amount of ordinary matter, but it doesn't fully explain the bizarre behavior we observe. The existence of dark matter and dark energy introduces fundamental questions about the underlying fabric of the universe, questions that the CMB alone cannot answer. Scientists hope that a deeper understanding of how these invisible forces interact with the CMB might eventually offer breakthroughs, shedding light on the most profound aspects of the universe's makeup. Additionally, as scientists continue to probe the CMB, they've encountered discrepancies between its measurements and those of other cosmic phenomena, such as the rate of expansion of the universe. This tension raises vital questions about our current models of cosmology and physics. How do these measurements fit together within the larger framework of cosmic evolution? The discrepancies between the CMB's predictions and observations related to the universe's expansion rate suggest that we may need new theories or adjustments to the existing ones. Each mystery within the CMB acts as a reminder of just how much we still have to learn about the cosmos, encouraging an ongoing quest for deeper understanding and new discoveries. Shifting from the study of the distant past to the potential of future travel, the concept of a wormhole offers an exciting and thought-provoking avenue for exploration. A wormhole is a theoretical structure in the fabric of space-time that could serve as a shortcut, connecting two distant points in space and time. Imagine, if you will, a vast three-dimensional universe where every location is separated by light years of distance. A wormhole in this context would provide a direct link between 2 points, allowing for instantaneous travel across distances that would otherwise take light thousands or even millions of years to traverse. To visualize this, think of 2 sheets of paper representing 2 locations in space. If you were to flatten them out, traveling from one to the other would involve crossing the entire distance between them. But if you were to bend and fold the sheets so the 2 points touch, you could simply cross over in an instant. This folding of space is analogous to how a wormhole would function, creating a tunnel through the very fabric of space-time itself. The idea of wormholes stems from the principles of Einstein's general theory of relativity, which explains how massive objects, like stars or black holes, warp space-time around them. This warping can lead to phenomena like black holes and, in theory, to wormholes as well. A wormhole, if it could be stabilized, would have 2 ends, one entrance and one exit. The entrance might resemble the mouth of a black hole, while the exit could emerge in a completely different region of the universe, or even in a different time. It's a fascinating concept, one that has captured the imagination of scientists and science fiction enthusiasts alike. However, it's important to note that, despite the elegance of the theory, no one has ever observed a wormhole in the real universe, and its existence remains speculative. Scientists continue to probe the laws of physics, seeking a deeper understanding of whether such structures can exist in reality. The challenges in maintaining a stable wormhole are formidable. One of the major obstacles is the potential for gravitational collapse. A wormhole, like a black hole, is subject to immense gravitational forces, and without the right conditions, it could collapse into singularity, essentially ceasing to exist. To keep a wormhole open, scientists believe that it would require an exotic form of matter, something not yet discovered, which would have unique properties, such as negative energy density. This exotic matter is crucial to preventing the wormhole from collapsing under its own weight. However, our current understanding of physics does not provide us with the knowledge to create or manipulate such matter, making the creation of a stable wormhole a daunting prospect. Despite these challenges, the concept of wormholes continues to captivate the imagination of researchers and the general public alike. The potential for instantaneous travel across vast distances, enabling us to explore alien worlds or visit distant stars, is an alluring possibility. Yet, as we stand on the frontier of this theoretical idea, the obstacles to making it a reality are as immense as the distances wormholes would allow us to traverse. Until new breakthroughs occur in physics, wormholes remain a fascinating but distant dream, a tantalizing glimpse into the future of space exploration. Imagine, if you will, a tunnel stretching across the vastness of space-time, a wormhole that defies our current understanding of physics. The mere thought of such a shortcut through the universe is enough to ignite the imagination, offering a tantalizing glimpse of a future where distances could be traversed in an instant. Yet, as alluring as this concept might be, there are serious concerns about the practical realities of traveling through such a phenomenon. While the potential for instantaneous travel could revolutionize our exploration of the cosmos, the dangers associated with it are far from trivial. Even if we could somehow stabilize a wormhole long enough to pass through it, The structural integrity of such a cosmic bridge remains questionable. The very fabric of space-time may not be able to withstand the immense forces exerted within the wormhole, creating a highly unstable environment. These forces, stemming from intense gravitational fields, could stretch or tear apart anything that dares to enter. This process, often referred to as spaghettification, would be akin to being pulled into an incomprehensible stretch of space, where every molecule is pulled apart along an axis. Just imagine the horror of traveling through a tunnel that might collapse at any moment, leaving you trapped in an unstable pocket of space-time. Additionally, even if a wormhole were stable enough to traverse, the problem of navigation looms large. Wormholes, if they exist, connect two separate points in space-time, but exactly where these points lead is anyone's guess. Just as finding the entrance to a cave doesn't guarantee a safe and predictable path through it, the same uncertainty applies to wormholes. You could emerge on the other side near a distant star, light years away from your intended destination. Or, perhaps worse, you might find yourself deposited in an entirely unknown and potentially hazardous region of the universe, where the laws of physics may not behave in familiar ways. The promise of rapid travel across vast distances may sound thrilling, but the unknowns are far too great for us to jump headfirst into this cosmic adventure. Theoretical physicists continue to wrestle with these challenges, knowing that wormholes offer a potential shortcut through space and time, but they are also acutely aware of the immense hurdles standing in the way. To make wormholes practical for space travel, we would need to understand the very nature of gravity, space-time, and the fundamental structure of the universe itself, topics that continue to elude even the brightest minds in science. For now, the dream of using wormholes for interstellar travel remains confined to the realm of theory, though it does continue to inspire both scientific research and the imagination. In the realm of science fiction, wormholes serve as a fascinating narrative tool, offering writers the ability to weave epic tales of adventure and exploration. These cosmic shortcuts allow fictional characters to cross vast distances in the blink of an eye, encountering strange new worlds, alien civilizations, and even alternate realities. While the scientific community remains cautious about the potential for wormhole travel, fiction has long embraced these portals as symbols of discovery, progress, and the boundless possibilities of the universe. From daring space operas to contemplative stories about the ethical dilemmas of traveling through time, wormholes become the vehicles of wonder and awe. Despite the lack of tangible evidence for the existence of wormholes, their conceptual significance continues to inspire and provoke thought. Scientists and writers alike are drawn to the idea of exploring the unknown and confronting the mysteries of space and time. Wormholes, in this sense, represent the cutting edge of both scientific inquiry and creative speculation, offering us a glimpse into the uncharted frontiers of the universe. Whether or not we ever develop the technology to harness wormholes for travel, they serve as a reminder that there is still so much we don't know about the cosmos. Questions yet to be answered, discoveries waiting to be made. Now, shifting focus to another mind-boggling cosmic phenomenon, the magnetar. This incredibly rare type of neutron star is one of the most extreme and fascinating objects in the universe. To fully appreciate the magnetar, we must first understand what a neutron star is. A neutron star forms when a star much larger than our sun runs out of fuel and collapses under its own immense gravity. This collapse creates a dense, compact object that is composed primarily of neutrons. The result is an object no larger than a city, but with a mass several times that of our sun. This extreme density makes neutron stars among the most fascinating objects in astrophysics. However, magnetars take things to an entirely new level. While regular neutron stars are known for their intense magnetic fields, magnetars possess magnetic fields that are far more powerful, trillions of times stronger than the Earth's magnetic field. This immense magnetic strength can have dramatic effects on the star itself and on its surroundings. These stars are so powerful that they can trigger bursts of energy in the form of X-rays and gamma rays, making magnetars some of the brightest and most energetic explosions in the universe. The magnetic field of a magnetar is not static, but grows over time due to the star's rapid rotation and the dynamic interactions within its dense core. This rotation generates an electric charge that amplifies the star's magnetic field, leading to a magnetic powerhouse that is beyond anything we can truly comprehend. When these magnetic forces reach critical levels, they can release violent bursts of radiation known as magnetar flares. These flares are so energetic that in just a matter of seconds, they can release more power than the sun will produce in its entire lifetime. The energy released in these bursts is not only astounding, but also incredibly dangerous. The radiation emitted, comprising primarily X-rays and gamma rays, can have significant effects on the environment around the magnetar. The effects of these flares are felt far beyond the magnetar itself. Objects near a magnetar can be subjected to intense radiation that can strip away their atmospheres, disrupt electronic systems, and even impact the evolution of surrounding bodies. For astronomers, studying magnetars provides a unique window into the most extreme astrophysical phenomena in the universe. Understanding how these stars function helps scientists learn more about the behavior of matter under extreme conditions, furthering our knowledge of the universe's fundamental laws. In many ways, magnetars represent the pinnacle of cosmic violence, where gravity, magnetism, and energy converge in a stunning display of natural forces. Though they are relatively rare, their study continues to challenge our understanding of the universe and push the boundaries of scientific knowledge. As we explore these celestial giants, we uncover new layers of mystery and intrigue, constantly reminding us of the vast and untamed nature of the cosmos. Through magnetars, we witness the forces that govern the universe at its most extreme, adding yet another layer of awe and wonder to our exploration of the stars. Magnetars, among the most extraordinary cosmic objects known to science, serve as one of the universe's most powerful magnetic phenomena. These neutron stars, which already exhibit magnetic fields far exceeding anything we experience on Earth, take that intensity to unimaginable extremes. To truly comprehend their sheer magnitude, imagine a typical neutron star, already an incredible entity by itself, whose magnetic field can be multiplied by several thousand times. What you get is the quintessential magnetar, a celestial powerhouse whose magnetic force can shape the environment around it in ways we are just beginning to understand. The immense magnetic fields surrounding magnetars have the ability to alter the behavior of matter and energy in their vicinity. In fact, these fields are so strong they can trap charged particles within them, leading to the creation of high-energy emissions known as magnetospheric bursts. Over time, however, the magnetic field of a magnetar may decay, weakening gradually. Despite this, it remains one of the most powerful magnetic entities in the universe, continuing to leave its mark on its surroundings, its host star, its neighboring objects, and even the very fabric of space itself. Understanding magnetars is not merely an academic pursuit, but a journey into the heart of cosmic mechanics. Their magnetic fields have the power to manipulate the behavior of nearby matter and light, which opens the door to studying dynamic astrophysical processes. For example, magnetars are known to produce jets of particles that shoot out from their surfaces, creating violent, high-energy displays. These jets, driven by the immense magnetic forces, reveal how magnetic phenomena can fuel activity on a cosmic scale. The study of magnetars also delves into some of the most extreme realms of physics. These objects provide a natural laboratory for understanding the interactions between magnetic fields and matter in states that are not found in other places within the universe. What happens to atoms and particles when exposed to magnetic fields stronger than any found in laboratories on Earth? How does matter behave under these conditions? These are just some of the fundamental questions scientists aim to answer. In addition to their magnetic properties, magnetars are known to produce intense bursts of energy, including X-rays and gamma rays, which travel across vast stretches of space and can be detected from light years away. These bursts offer valuable insights into the life cycles of stars and their ultimate demise, further enriching our understanding of stellar evolution. The study of these cosmic giants thus not only provides clarity on the nature of magnetism, but also reveals the complex processes that govern the universe's evolution. Within the magnetar's study lies another fascinating domain, the phenomena of fast radio bursts, FRBs. These high-energy bursts of radio waves, though lasting mere milliseconds, can release as much energy as hundreds of millions of suns. Discovered somewhat serendipitously in 2007, FRBs have since intrigued astronomers due to their unpredictable nature and brevity. These flashes appear sporadically, sometimes for only a fraction of a second, and have become a major puzzle for astrophysicists. The mystery of FRBs lies not only in their fleeting duration, but also in their origins. Though many of these bursts have been detected, their exact sources remain a subject of intense speculation and study. Some astronomers suspect they may be originating from distant galaxies, but the exact mechanisms driving these high-energy bursts are still largely unknown. Proposed theories range from the collapse of stars to the interactions between neutron stars, which are the remnants of exploded stars and among the densest objects in the universe. Adding to the complexity of FRBs is the fact that some of these bursts repeat, while others only occur once, further deepening the mystery of their true nature. In fact, some FRBs have been detected multiple times, which gives scientists a chance to study them more closely, while others seem to emerge only once, leaving behind even more unanswered questions. The journey of these bursts from their source to Earth is equally intriguing. Traveling vast distances through the cosmos, these radio waves must pass through the intergalactic medium, the space between galaxies, where they encounter dust, gas, and plasma. This journey is not without consequence. The signal can become distorted or altered in particular ways, providing astronomers with valuable insights into the composition and evolution of the universe itself. Studying these distortions can reveal information about the universe's structure, offering clues about how it has changed over billions of years. The allure of FRBs lies in their energetic output and mysterious origins. Each burst packs an immense punch, releasing as much energy in a few milliseconds as the sun does in an entire day. Such extraordinary power prompts a number of questions. What could possibly generate these bursts of energy? Some theories suggest the collision of neutron stars or other catastrophic events in space. Others go even further, proposing that these bursts could be the result of interactions involving black holes, or more speculatively, the work of advanced extraterrestrial civilizations. While the last theory is certainly outlandish, the study of FRBs remains a powerful tool for expanding our understanding of the cosmos. As the study of fast radio bursts continues to evolve, these events challenge our conventional understanding of stellar life cycles and extreme astrophysical phenomena. Their existence pushes the boundaries of what we know about the universe, forcing us to reconsider even the most fundamental aspects of physics. In this way, FRBs serve as a kind of cosmic riddle, one that offers new opportunities for discovery and exploration. Moreover, these enigmatic signals are not limited to FRBs alone. A multitude of other cosmic phenomena, such as gamma-ray bursts and supernova explosions, also produce detectable signals that travel across billions of light years. These extreme events create shock waves and radiation that can be observed across different wavelengths, providing additional layers of information about the workings of the universe. However, the study of these signals is not without its challenges. Earth's atmosphere, interference from satellites, and even cosmic background radiation can distort or obscure the signals we receive, complicating our efforts to determine their true origins. Scientists must account for these factors as they work to piece together the puzzles that space presents. In the end, each proposed source for these mysterious signals offers intriguing insights into the workings of the universe. Whether it's the possibility of rapidly spinning neutron stars emitting beams of radiation, or the potential that FRBs are somehow connected to extraterrestrial technologies, every new discovery brings us one step closer to understanding the vast, complex nature of the cosmos. As our ability to detect and interpret these signals improves, we continue to unravel the mysteries of space, revealing a universe more dynamic and fascinating than we ever imagined. With each breakthrough in this phenomena, we uncover new layers of knowledge about the universe, its origins, and its evolution. The more we learn, the more we realize how much we still have yet to discover. Each mystery solved opens the door to even greater unknowns, driving humanity's curiosity and quest for understanding ever forward. The occurrence of fast radio bursts, FRBs, presents a fascinating and perplexing challenge for astronomers, raising numerous questions about their nature and distribution. These bursts, brief yet incredibly intense bursts of radio waves, appear to pop up seemingly out of nowhere. However, their exact rate of occurrence and whether they emerge in random bursts or follow identifiable patterns remains unknown. Investigating these phenomena further could provide critical insights into the fundamental structure of the universe, and in particular, help astronomers map the cosmos with greater precision. By revealing patterns or trends in the distribution of FRBs, we could begin to understand not just their origins, but also the larger forces at play across the universe. This data holds the potential to unlock new models of galactic evolution, enabling us to better track the birth and death of galaxies across time. Given that FRBs were first detected only in recent years, they push the boundaries of our understanding of astrophysics. Their discovery is akin to opening a new chapter in the story of the universe, urging researchers to delve deeper into their origins. Are these bursts the result of extreme phenomena happening in distant galaxies, or do they signify something even more profound about the forces that shape our universe? As astronomers study these signals, the questions multiply, drawing us into a complex investigation that challenges everything we thought we knew about the fabric of space and time itself. Within galaxies, there are a variety of strange and unexplained phenomena that continue to spark intense curiosity. Perhaps one of the most elusive and intriguing mysteries is that of dark matter. Despite its invisible nature, dark matter makes up the majority of the mass within galaxies. It neither emits nor reflects light, making it entirely undetectable by conventional means. Yet, without it, galaxies would not hold together. The gravitational pull of this unseen substance prevents galaxies from flying apart as they spin at incredible speeds. Without dark matter, the universe as we know it would be drastically different. Though we can't observe dark matter directly, its existence is inferred from the way galaxies move and behave. Similarly, the discovery of supermassive black holes at the centers of many galaxies, including our own Milky Way, adds another layer of complexity to our understanding of cosmic evolution. These immense objects, which are millions or even billions of times more massive than the Sun, continue to intrigue and baffle scientists. How did they form, and what role do they play in the development of galaxies? Are they the result of gravitational collapse, or is their formation tied to the merging of multiple smaller black holes over eons? Their impact on their host galaxies is undeniable. As supermassive black holes grow, they influence star formation, galaxy dynamics, and even the large-scale structure of the universe. Another curious phenomenon that draws the attention of astronomers is the behavior of variable stars. These stars experience fluctuations in brightness, a trait that can be attributed to a variety of factors, from pulsations within the star itself to interactions with neighboring stars. The causes of these fluctuations provide valuable clues about stellar life cycles, allowing scientists to better understand the forces that govern stellar birth, evolution, and death. Some variable stars may even undergo dramatic transformations, turning into supernovae or collapsing into black holes, events that dramatically alter the landscape of their host galaxies. Beyond individual stars, galaxies themselves can harbor peculiar structures known as cosmic filaments. These vast, interconnected strands of gas and dark matter form the skeleton of the universe, connecting clusters of galaxies across unimaginable distances. These enormous structures suggest a large-scale cosmic web that links together vast regions of space. Understanding how these filaments formed and the forces that shaped them could reveal much about the early universe and the processes that govern its evolution. The study of these filaments, along with the forces that hold them together, remains a topic of intense research. At the other end of the spectrum, there are phenomena such as gamma-ray bursts, powerful and incredibly energetic explosions that occur in distant galaxies. These bursts emit vast amounts of energy, often brighter than entire galaxies combined. Their origins are still not fully understood, but scientists believe they may signal the birth of a black hole or the merger of neutron stars. The mechanisms behind these bursts remain one of the greatest mysteries in astrophysics. What exactly happens during these explosive events? How do they release so much energy? And what can they teach us about the evolution of galaxies and the forces that govern their behavior? Each of these unexplained phenomena opens a new window into understanding the cosmos, inviting astronomers to dig deeper into the mysteries of the universe. Whether it's the search for dark matter, the study of black holes, or the investigation of cosmic filaments and gamma-ray bursts, each discovery leads us one step closer to comprehending the vast and complex forces that shape the cosmos. These events, whether large or small, tell a story of the universe's inner workings, one that is far more dynamic and interconnected than we might ever have imagined. Imagine a galaxy as a living, breathing entity, one that is constantly being shaped and transformed by powerful and often unpredictable forces. Events such as supernova explosions, the collision of galaxies, and the growth of supermassive black holes play a significant role in this ongoing transformation. These occurrences are not just fleeting moments in the life of a galaxy. They are pivotal moments that shape the very future of the galaxy itself. When a massive star reaches the end of its life, it often explodes in a brilliant supernova, releasing an enormous amount of energy. This explosion is not just a spectacular display of light and power. It also serves as a crucial part of the cosmic recycling process. Supernovae enrich the surrounding gas clouds with heavy elements which were forged in the star's core. These elements then become part of the interstellar medium, where they will eventually form new stars, planets, and even life. In this way, supernovae are the cosmic agents of creation, fueling the birth of new celestial bodies and continuing the cycle of stellar life. Similarly, when two galaxies collide, the results are often dramatic. Imagine two massive galaxies gracefully merging, their stars, gas, and dust intermingling in a spectacular dance. This interaction sparks a flurry of new star formation, and over time, the galaxy's structures are altered beyond recognition. The collision can also trigger the growth of supermassive black holes at their centers, a process that can further shape the evolution of the newly merged galaxy. These galactic collisions are not mere accidents. They are integral moments in the life cycle of galaxies, contributing to their development over billions of years. Such phenomena, whether the explosive birth of a new star or the merging of two galaxies, challenge our understanding of how galaxies evolve. They raise questions about the forces that drive cosmic change, the role of black holes, and the ways in which galaxies interact with each other. As astronomers continue to study these events, they are beginning to see that the evolution of galaxies is not a smooth, gradual process, but one marked by dramatic moments of transformation. Each explosion, collision, or unexpected event is a chapter in the ongoing saga of the universe. At the heart of our own Milky Way galaxy lies a region that has long captivated scientists and astronomers alike. In the center of this region lies Sagittarius A, a supermassive black hole whose mass is estimated to be millions of times that of our Sun. This black hole, with its immense gravitational pull, exerts a profound influence on the orbits of nearby stars. The discovery of Sagittarius A star has provided astronomers with an invaluable laboratory for studying the behavior of supermassive black holes and their impact on the surrounding galaxy. It also raises fundamental questions about the formation and evolution of these cosmic giants, as well as the role they play in shaping the destiny of galaxies. As we continue to explore and study the strange and enigmatic phenomena that lie within galaxies, we uncover ever more complex and intriguing aspects of the universe. Whether it's the unexpected bursts of energy from distant galaxies or the formation of new stars in the wake of supernova explosions, every discovery brings us closer to understanding the grand and intricate dance of the cosmos. In recent years, researchers have uncovered a series of groundbreaking discoveries in our understanding of the center of the Milky Way, a region that has long been associated with mystery and intrigue. At the heart of this galactic center lies a supermassive black hole, the forces surrounding which have traditionally been thought to make star formation impossible. However, recent findings have completely challenged this assumption. In fact, scientists have found evidence of numerous young, massive stars in the vicinity of the black hole, an astonishing revelation that suggests this hostile environment is far more dynamic than previously believed. Rather than being a barren, inhospitable zone, the area surrounding the black hole appears to support the formation of new stars, despite the extreme conditions at play. The forces near the galactic core are not just destructive, but complex and active, offering a more intricate picture of the dynamics at work. One of the most captivating discoveries in this region involves the high-energy phenomena emitted by the black hole, including powerful jets and outflows. These jets can extend across vast distances, streaming material outward at unimaginable speeds. The forces behind these jets are both awe-inspiring and puzzling, as they play a significant role in regulating star formation within the galaxy. By dispersing gas and dust in intricate patterns, these outflows help shape the very structure of the Milky Way. The interplay between these powerful forces and the formation of stars is one of the most remarkable features of this galactic center. But perhaps even more intriguing is the discovery of a complex gas cloud structure, which includes a massive, thin cloud that continues to baffle researchers. These gas clouds exhibit strange and unpredictable behaviors, moving at varying speeds and directions that defy expectations. The study of these clouds has provided deeper insight into the turbulent environment near the galactic center, suggesting that the forces at play are far more varied and dynamic than anyone had imagined. The discovery of these structures is a testament to the ongoing complexity of this region, highlighting just how much remains to be understood. As a whole, the center of the Milky Way is far from being a static, lifeless void dominated solely by a supermassive black hole. Instead, it is an active, vibrant region filled with star formation, high-energy phenomena, and complex interactions. Each new discovery adds another layer to our understanding of the universe, revealing how the forces at the heart of the galaxy influence the entire structure and dynamics of the Milky Way. These insights continue to deepen our appreciation for the complex nature of the universe and the intricate relationships between stars, black holes, and the vast interstellar medium that binds them together. Meanwhile, on Earth, scientists have been working tirelessly to explore one of humanity's most profound questions. Are we alone in the universe? The search for extraterrestrial life is one of the most exciting and challenging scientific endeavors, and it takes many forms. One of the primary methods used to search for life beyond Earth is the study of exoplanets, planets that orbit stars other than our Sun. Using increasingly advanced telescopes, astronomers have been able to observe these distant worlds, searching for signs that could suggest the presence of life. Key indicators, such as the presence of carbon dioxide and oxygen in a planet's atmosphere, are often associated with biological processes here on Earth, making them important markers in the search for life elsewhere. In addition to this observational approach, robotic missions are being sent to various planets and moons within our own solar system. These missions, such as those exploring the surface of Mars or the icy moon Europa around Jupiter, collect soil and ice samples in the hope of discovering organic compounds, the basic building blocks of life. The detection of water, especially liquid water, is another major focus, as scientists believe that water is an essential ingredient for life as we know it. These missions help to expand our understanding of the potential for life in environments that are drastically different from Earth, yet might still harbor the conditions necessary for life to thrive. The search for extraterrestrial life also involves the use of radio telescopes in an effort to detect signals from advanced civilizations beyond Earth. This branch of the search, known as the Search for Extraterrestrial Intelligence, SETI, aims to pick up any artificial signals that might stand out against the natural background noise of the universe. The hope is to find evidence of technological activity, signals that would indicate the presence of intelligent life somewhere in the cosmos. In addition to these direct searches, scientists also rely on theoretical models and simulations to help guide their search. Astrobiology, the study of life in the universe, is a critical part of this effort. By studying extreme environments here on Earth, such as the deep ocean vents or acidic lakes, scientists can develop a better understanding of the kinds of conditions that might support life on other planets or moons. These studies allow researchers to expand the potential range of environments where life might exist, and to explore what forms that life might take. The quest to find extraterrestrial life is about more than just the search for alien organisms. It is a quest to understand our own place in the universe. The discovery of life beyond Earth would be a profound event, one that would challenge our very understanding of biology, evolution, and even the nature of life itself. For centuries, humanity has pondered the question of whether we are alone in the cosmos, and now, with each new discovery, that question seems more pressing than ever. As we learn more about distant exoplanets, moons, and other celestial bodies, the possibility that life exists elsewhere becomes increasingly tantalizing. Such discoveries would not only alter our scientific understanding, but would also have deep philosophical and existential implications. The knowledge that life exists elsewhere could redefine our sense of uniqueness and our place in the universe. It might suggest that life is not a rare phenomenon, but rather something that emerges under the right conditions across the cosmos. From the icy moons of distant planets to the lush environments of alien worlds, life could be flourishing in places we have yet to even imagine. Moreover, the discovery of extraterrestrial intelligence would have even more far-reaching consequences. If we were to encounter a civilization with technology far beyond our own, it could lead to exchanges of knowledge and culture that could completely transform our understanding of science, philosophy, and ethics. The insights and perspectives gained from such an interaction would likely be invaluable, offering new ways of thinking about the nature of intelligence, consciousness, and the very essence of existence. Despite the immense distances, technological limitations, and the many challenges involved in the search, the quest for extraterrestrial life continues to captivate and inspire. The mysteries surrounding this search are as vast as the universe itself, and each new discovery brings us closer to unraveling the question of whether we are alone. At the same time, these discoveries deepen the mystery, reminding us of how much we still have to learn. The quest for extraterrestrial life is not just about finding other beings. It is about understanding our place in the grand, awe-inspiring expanse of the cosmos. The discovery of extraterrestrial life, if it were to occur, would be a groundbreaking moment in human history. It would transform our view of the universe in ways we can only begin to imagine. Currently, we view Earth as a unique oasis in a vast and empty cosmic sea. But the discovery of life elsewhere would suggest that life is far more common than we ever thought. Such a revelation would likely reshape our understanding of the conditions necessary for life: water, organic compounds, and the right atmospheric conditions, indicating that these ingredients might be prevalent throughout the cosmos. Ultimately, finding life beyond Earth would prompt a profound shift in how we view ourselves. We might begin to see ourselves not as the pinnacle of life's evolution, but as part of a much larger cosmic community. This realization could inspire deep reflections on the nature of life, intelligence, and consciousness, reshaping not only our scientific understanding, but also our philosophical and moral perspectives. In the end, the quest to find extraterrestrial life is a journey that takes us not just to the stars, but into the very heart of who we are as a species, offering new insights into the mysteries of life itself. The intricate ways in which life forms adapt and survive in extreme conditions offer not only a glimpse into the resilience of life, but also present the potential for groundbreaking scientific advancements. By studying diverse life forms, many of which exist in environments far harsher than those we can easily comprehend, we might unlock secrets of biology, evolution, and survival. These insights could propel our understanding of our own species, while simultaneously deepening our comprehension of the future of life on Earth. Every discovery could lead to fresh ideas, transforming everything from medicine to sustainable practices. Moreover, the implications of this research are not confined to biology alone. The study of these resilient life forms may also push the boundaries of technological innovation and communication. If we were to encounter intelligent life forms beyond Earth, understanding how they perceive the universe could challenge our very conceptions of reality. They may think, communicate, and experience existence in ways completely alien to us. The exploration of these complex interactions could force us to rethink technological priorities, ethics, and cooperation on a global scale. We could find ourselves questioning not only how we reach out to these extraterrestrial beings, but how we might better communicate and collaborate within our own species. Finding life beyond Earth, if it exists, would alter our understanding of our place in the universe, igniting new possibilities for the future of humanity. One of the most fascinating phenomena that connects space with life on Earth is the cosmic ray. These high-energy particles, which travel through the vastness of space, have the ability to reach our planet from deep within the cosmos. Primarily composed of protons, though they can also include heavier atomic nuclei and even electrons, cosmic rays are like messengers from the farthest reaches of the universe. They carry with them not just the imprint of their origin, but also valuable information about the processes taking place across the cosmos. Most of these cosmic rays come from our sun, particularly during periods of heightened solar activity, such as solar flares. However, many of the highest energy cosmic rays have far more dramatic and exotic origins. It is believed that these high energy particles are produced by catastrophic events such as supernova, the explosive deaths of massive stars, or by the enormous jets emitted from black holes as they consume surrounding material. These cosmic events act as cosmic factories, accelerating particles to unimaginable speeds and sending them on a long journey across the universe. Yet the path of these particles is anything but straightforward. As they travel through space, cosmic rays encounter magnetic fields from distant galaxies that can warp and bend their trajectories. These disturbances complicate efforts to trace their origins, making it difficult to determine exactly where they come from. When cosmic rays reach Earth, they interact with our atmosphere, producing showers of secondary particles that cascade downward, reaching the surface of the planet. This phenomenon creates a constant rain of cosmic particles, which is one of the primary ways scientists can detect cosmic rays. The study of these cosmic rays provides valuable insight into high-energy processes occurring across the universe. By observing how cosmic rays interact with Earth's atmosphere and the resulting secondary particles, scientists are able to examine the nature of the universe's most energetic events, as well as the particles themselves. This research helps to deepen our understanding of astrophysical phenomena such as supernovae, black holes, and the fundamental forces shaping the cosmos. Moreover, these cosmic rays can offer clues about the nature of the universe's most mysterious processes, providing scientists with invaluable data to unravel some of the greatest mysteries of space and time. However, cosmic rays are not merely an abstract scientific curiosity. They also have direct implications for life and technology on Earth. One of the most concerning aspects of cosmic rays is their potential to cause harm to living organisms. As these high-energy particles pass through the Earth's atmosphere and interact with biological tissues, they can inflict damage at a cellular level. This damage can disrupt cellular structures and lead to mutations in DNA, increasing the risk of cancer and other diseases over time. Fortunately, Earth's atmosphere, along with its magnetic field, serves as a protective shield, mitigating much of the damage caused by these cosmic rays. Nevertheless, certain individuals, such as astronauts and pilots who spend extended periods of time at high altitudes, are exposed to higher doses of cosmic rays, making their study crucial for understanding the potential health risks associated with such exposure. The technological ramifications of cosmic rays are equally significant. Satellites, for example, are particularly vulnerable to cosmic rays. These energetic particles can collide with sensitive components in satellites, causing malfunctions or errors. This is known as the radiation effect, and it can result in data loss, communication failures, or even the complete shutdown of satellite systems. To mitigate these risks, engineers design satellites with protective shielding and error-correcting codes to guard against the interference caused by cosmic rays. The potential for cosmic rays to disrupt technologies essential to modern life, such as communication networks, navigation systems, and weather monitoring, is a critical area of ongoing research and development. Despite the challenges cosmic rays present to life and technology on Earth, they also play a crucial role in advancing scientific knowledge. Researchers harness the energy of these particles to study the universe, exploring not only the phenomena that produce them, but also testing theories about the fundamental particles that make up the fabric of the cosmos. By studying the composition and behavior of cosmic rays, Scientists are able to learn more about the processes that accelerate particles to such extreme energies. This dual nature of cosmic rays, as both a potential threat to life and technology and a powerful tool for scientific discovery, underscores the complex relationship between space and life on Earth. The mystery surrounding the origins of cosmic rays continues to captivate the scientific community. While some cosmic rays are believed to originate from supernova explosions, the majority of high-energy cosmic rays seem to come from unknown sources. This leaves scientists with numerous questions. What are these sources? What forces are responsible for accelerating these particles to such incredible speeds? The nature of cosmic rays remains one of the most tantalizing puzzles in modern astrophysics. Another significant area of curiosity involves the composition of cosmic rays. Although they are primarily composed of protons, the building blocks of atomic nuclei, cosmic rays can also contain heavier atomic nuclei and even electrons. Understanding the relative abundance of these components can provide crucial information about the origins of cosmic rays and the processes responsible for their acceleration. For example, the presence of heavier atomic nuclei could indicate that the cosmic rays are produced in extremely high-energy environments, such as the aftermath of a supernova or the vicinity of a black hole. The journey of cosmic rays through space adds yet another layer of complexity. As they travel across the universe, cosmic rays interact with magnetic fields from galaxies, bending and distorting their paths. This makes it incredibly difficult to trace their origins. By the time they reach Earth, cosmic rays are often part of a cascade of secondary particles, further complicating efforts to study them. Despite these challenges, scientists continue to probe the mysteries of cosmic rays, working to unlock the secrets they hold about the universe's most energetic and enigmatic phenomena. In conclusion, the study of cosmic rays represents an intersection of multiple scientific fields, from astrophysics to biology and technology. These particles, traveling through the cosmos at nearly the speed of light, provide valuable insights into the most powerful forces in the universe, while also posing risks to life and technology on Earth. As our understanding of cosmic rays continues to evolve, so too will our comprehension of the universe itself and our place within it. Furthermore, the energies of these particles exceed anything that could be achieved within the confines of human-made particle accelerators, pushing the boundaries of what we believe to be physically possible. This creates a compelling and perplexing mystery. How are such extreme energies generated? The standard laws of physics, as we know them, struggle to account for these phenomena, and with each new discovery, the anomaly becomes more pronounced. The known universe seems to be challenging our most fundamental understanding of physics, and the quest to unlock the secrets of these particles brings with it a wave of hypotheses. Scientists now speculate that exotic, as yet undiscovered processes may be at work, possibly involving forces or phenomena that remain hidden in the deepest recesses of space-time. This journey into the world of high-energy particles has become one of the most exciting frontiers in modern science. Every new discovery presents more questions than answers, and this process of discovery pushes the limits of both theory and technology. With each step forward, new observational methods and more advanced technology offer us glimpses into these high-energy environments, slowly bringing us closer to understanding the true nature and origins of these cosmic messengers. Gravitational anomalies present another fascinating challenge in the exploration of our universe. These anomalies manifest as unexpected variations in gravitational pull, either stronger or weaker than we would expect, based on the mass distribution of Earth, or in the vastness of space itself. Gravitational anomalies have been observed in a number of locations across the planet and even beyond Earth's surface. For instance, in the Bermuda Triangle, there have been consistent reports of unusual fluctuations in gravity, which some speculate could be responsible for the mysterious behavior of ships and aircraft that vanish without a trace in that region. Similarly, gravitational anomalies have been documented in the Hudson Bay area of Canada, where the gravitational pull appears weaker than in surrounding areas. This anomaly is believed to be the result of glacial melting, where the redistribution of mass caused by the retreat of glaciers has left a noticeable imprint on Earth's gravitational field. Gravitational anomalies extend far beyond the Earth's surface, reaching into the far corners of our solar system. In space, scientists have observed similar inconsistencies in the gravitational forces surrounding celestial bodies, such as the Moon. Some regions of the Moon exhibit gravitational pull that is stronger or weaker than expected. These fluctuations provide valuable insights into the Moon's geological history and its internal structure. The study of such anomalies allows scientists to probe deeper into the composition and history of not just the Earth, but other celestial bodies as well. These anomalies are powerful windows into the intricacies of gravity, revealing hidden geological features and helping us understand the distribution of mass in ways that traditional methods cannot. When we consider gravity itself, we typically envision it as a constant force, pulling objects toward one another. This force is responsible for everything from the fall of an apple to the orbits of distant planets. Yet, as researchers delve deeper into the behavior of the universe, it becomes increasingly clear that gravity may not be as straightforward as we once thought. In particular, the way galaxies behave challenges our traditional view of gravity. Scientists have observed that galaxies rotate in ways that cannot be explained solely by gravitational forces. The outermost stars within these galaxies spin at speeds that, according to current models, should cause them to fly off into space, not remain bound together. This paradox has led to the development of new theories, one of the most prominent being the concept of dark matter. Dark matter is an invisible substance that, despite not interacting with light, exerts gravitational forces that influence the motion of galaxies. While it remains undetectable by conventional means, its presence is inferred by the effect it has on visible matter. This revelation adds a new layer to our understanding of gravity, suggesting that the force may not operate in isolation. There could be hidden factors, forces, or particles we have yet to identify that are modifying how gravity behaves on a cosmic scale. This idea forces us to reconsider everything we thought we knew about the force that binds the universe together. Moreover, the extreme conditions near black holes and neutron stars present further challenges to our understanding of gravity. These objects possess incredibly intense gravitational fields that warp space-time in ways that break down even the most robust models of physics. The behavior of gravity in these environments is difficult to predict, leading scientists to question whether gravity is a consistent force or whether it can vary under different circumstances. Can gravity behave differently near such massive objects, or is it something that operates consistently throughout the universe? These anomalies force scientists to reevaluate their theories, opening the door for new possibilities and encouraging the exploration of alternative explanations. This ongoing investigation into the nature of gravity and other cosmic forces is vital to our understanding of the universe. These anomalies not only challenge our knowledge of fundamental physics, but also prompt us to think in new ways. As technology improves, we may come to realize that our view of the cosmos is far more complex than we ever imagined. In many ways, these anomalies act as a catalyst for scientific innovation, inspiring new theories, developing new technologies, and pushing the limits of human understanding. The impact of such anomalies extends far beyond academic curiosity. It plays a significant role in how we approach future space exploration. Discovering unexpected phenomena in space forces us to reevaluate our current models of the universe's mechanics. If scientists detect gravitational forces that cannot be explained, or if we observe objects behaving in ways that defy current theories, this compels us to refine our approach to space exploration. Such discoveries could lead to advancements in technology such as more accurate navigation systems or better communication tools, allowing us to function more efficiently in the vast and unpredictable expanse of space. Understanding these anomalies also holds the potential to revolutionize our approach to future missions. If certain regions of space exhibit unusual properties, whether in terms of gravitational forces, radiation, or the presence of materials, we may begin to identify target locations for future exploration. For example, certain areas may hold the promise of untapped resources or the potential for life-sustaining elements, making them prime candidates for exploration. The very nature of these anomalies may influence the kinds of missions we prioritize and shape the training and equipment we develop for astronauts to navigate these challenging environments. Beyond the practical implications, the study of anomalies can also spark a broader sense of curiosity and cooperation within the global scientific community. As countries and institutions collaborate on addressing these mysteries, they will expand our collective knowledge, creating new opportunities for discovery and pushing the boundaries of space exploration. This collective effort is essential to broadening our understanding of space and ensuring that we are prepared for the challenges that lie ahead. The insights gained will not only guide future missions, but will also serve to inspire future generations of scientists, engineers, and explorers to pursue even greater discoveries. In addition to these more tangible effects, the exploration of anomalous phenomena may also lead us to uncover entirely new forces and forms of matter that we have never before imagined. One such concept is dark energy, a mysterious, invisible force that is believed to be driving the accelerated expansion of the universe. While its existence is well supported by observational data, its true nature remains one of the most elusive questions in modern science. Dark energy seems to act like a kind of cosmic repulsion, pushing galaxies away from each other. Yet scientists still have little understanding of what it actually is or how it works. Similarly, the enigma of dark matter continues to fascinate researchers. Though it is believed to account for a significant portion of the mass in the universe, it does not emit or interact with light, making it undetectable by traditional observational methods. Despite this, its gravitational influence is clear, as it plays a crucial role in binding galaxies together. The composition of dark matter remains a mystery, with many scientists hypothesizing that it could be made of particles that we have yet to discover. Additionally, the idea of extra dimensions in the universe adds another layer of intrigue to our understanding of the cosmos. We are accustomed to thinking in terms of 3 spatial dimensions and 1 temporal dimension, but some theories suggest that there may be additional dimensions beyond these 4. These extra dimensions could harbor unknown forces or particles, expanding the limits of our current understanding of the universe. One of the most fascinating concepts related to this is string theory, which posits that the fundamental building blocks of the universe are not individual particles, but tiny, vibrating strings. If proven true, this theory could fundamentally change the way we understand the nature of matter, energy, and the very fabric of space-time itself. As we continue to explore the mysteries of gravity, dark matter, dark energy, and the very structure of the universe, we are not only expanding the boundaries of scientific knowledge, but also redefining the nature of reality itself. These unexplained phenomena and anomalies challenge the very foundation of our understanding, and in doing so, they drive the scientific community to innovate, collaborate, and push the limits of what is possible in the quest for knowledge. The universe is far more complex than we once believed, and with each new discovery, we inch closer to understanding the forces and mechanisms that govern the vast expanse of space. The exploration of manipulating gravity has become a captivating frontier in modern scientific inquiry. Gravity, one of the 4 fundamental forces that govern our universe, has long been a force of nature we take for granted. Yet, delving into the realm of its manipulation raises profound questions that could one day redefine not only the way we understand physics, but also revolutionize our technological advancements. What if we could harness gravity, the very force that binds planets to their orbits and governs the flow of time itself? Such ideas belong to the realm of cutting-edge science, where theoretical explorations of gravity's potential manipulation could pave the way for unimaginable breakthroughs, including space travel and beyond. These speculative theories about altering gravity do more than simply push the boundaries of our scientific imagination. They challenge our current understanding of the physical laws that govern everything from the movement of galaxies to the interaction of subatomic particles. Each theory about potential new forces, whether related to gravity or other hypothetical interactions, invites profound reflection on our place in the cosmos and the limits of what we can comprehend. At the heart of this speculative science lies the tantalizing possibility that we may one day discover forces yet unknown to us. forces that might change the entire paradigm of physics. The potential discovery of new forces, especially one that could allow the manipulation of gravity, would herald an era of transformative exploration. Our present understanding of the universe is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These four forces provide the framework for nearly every phenomenon in nature, from the motion of celestial bodies to the behavior of subatomic particles. If a new force were to be discovered, it would compel scientists to revisit and perhaps revise many of our core theories in physics. This new force could offer a glimpse into previously unseen interactions or forces that we have misinterpreted, overlooked, or not yet discovered. In doing so, it could unlock answers to some of the most enigmatic aspects of the universe, such as the mysterious phenomena of dark matter and dark energy, two concepts that remain elusive despite forming a substantial portion of the observable universe. The implications of discovering such a force would not be confined to the realm of theoretical physics. The consequences would ripple across multiple scientific domains, touching fields like cosmology, energy research, and even the fundamental nature of space and time itself. Imagine, for instance, a new force that could allow us to manipulate energy in ways we currently cannot fathom, perhaps enabling the development of technologies that are now firmly in the realm of science fiction. Moreover, the impact could extend far beyond the laboratory. It could reshape our understanding of how the universe works on every scale, from the microscopic to the cosmic. However, integrating such a new force into our existing scientific models would not be a simple process. It would require extensive experimentation, validation, and potentially a fundamental reevaluation of established physical laws. Physicists would need to develop new frameworks that incorporate this new force into the broader tapestry of science, conducting tests and experiments to validate its existence and understand its behavior. This process would likely involve challenging the assumptions we have held for centuries about the nature of reality itself. Through this process of discovery and experimentation, we would be pushed to think more creatively about the universe and our role within it. As we explore the possibilities of new forces, we could uncover entirely new dimensions of the cosmos that were previously unimaginable. One of the most active areas of research today revolves around understanding the invisible forces that seem to shape the universe. Dark matter and dark energy, which together constitute a vast majority of the universe's mass and energy, remain among the greatest mysteries in modern science. Unlike ordinary matter, which interacts with light and can be observed through telescopes, dark matter does not emit or absorb light, making it nearly impossible to detect through traditional means. However, scientists are developing increasingly sophisticated ways to probe these hidden forces. One method involves constructing highly sensitive detectors deep underground, shielded from cosmic radiation and other sources of noise. These detectors are designed to capture the faintest signals from dark matter particles, which may be responsible for gravitational effects observed in galaxies and galaxy clusters. At the same time, astronomers are studying the effects of dark energy, another mysterious force thought to be driving the accelerated expansion of the universe. By examining the light from distant supernovae, which act as cosmic beacons marking the death of stars, scientists can observe how the brightness of these explosions changes over time. This data provides insights into the rate at which the universe is expanding, and much of this expansion is attributed to dark energy, a force that works counter to gravity on the grandest scales. While dark matter exerts its influence through gravity, dark energy acts as an opposing force, accelerating the universe's expansion at an ever-increasing rate. Another critical avenue of experimentation involves particle accelerators, which aim to recreate the extreme conditions that existed just after the Big Bang. By smashing particles together at velocities close to the speed of light, physicists can simulate the high-energy environment of the early universe, hoping to uncover new particles or interactions that could provide clues about dark matter. The Large Hadron Collider, LHC, the world's most powerful particle accelerator, is a key facility in this search for new forces. Researchers at the LHC are exploring how fundamental particles behave under extreme conditions, potentially unlocking new insights into the nature of dark matter and dark energy. In addition to these particle experiments, gravitational wave detectors are providing an entirely new window into the universe. These sensitive instruments detect ripples in space-time caused by massive cosmic events, such as the collision of black holes or neutron stars. These ripples, known as gravitational waves, allow scientists to observe phenomena that were once invisible, offering a fresh perspective on the dynamics of the cosmos. The detection of gravitational waves has already yielded groundbreaking discoveries, but it may also provide new clues about the role of dark energy in shaping the universe. All these experiments, in their diversity and complexity, contribute to a larger puzzle. They are helping us to unravel the hidden forces that influence the universe, and through them we may one day glimpse the full picture of how reality is structured. Each experiment opens a new door, shedding light on the fundamental forces of nature and expanding our understanding of the cosmos. The theory of an expanding universe, long accepted by scientists, is supported by a wealth of evidence accumulated over many years. One of the most compelling pieces of evidence comes from the observation of distant galaxies. When scientists examine the light emitted by these galaxies, they observe a phenomenon known as redshift. The light shifts toward the red end of the spectrum. This shift occurs because these galaxies are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This observation, first made by astronomer Edwin Hubble in the 1920s, led to the realization that the universe is expanding, with galaxies moving away from each other over time. Another crucial piece of evidence comes from the cosmic microwave background radiation, which is a faint glow that fills the universe. This radiation is a relic of the Big Bang, the cataclysmic event that marked the beginning of the universe as we know it. The cosmic microwave background radiation provides a snapshot of the early universe, offering clues about its temperature and structure shortly after its creation. The temperature of this radiation matches predictions made by the theory of an expanding universe, further supporting the idea that the universe has been stretching and cooling ever since the Big Bang. As scientists continue to probe these mysteries, they are uncovering new aspects of the universe's past, present, and future. From understanding the forces that shape galaxies and stars to uncovering the hidden dimensions of space-time, these explorations are pushing the boundaries of human knowledge, opening new frontiers in our quest to understand the deepest laws of nature. The distribution of galaxies across the universe offers compelling evidence for its expansion, and by examining large-scale structures, we gain a deeper understanding of the dynamic processes shaping the cosmos. Galaxies are not randomly scattered. Instead, they form intricate patterns, clumps, clusters, and vast filaments. These structures reveal the profound influence of gravity on the distribution of matter over cosmic time. The organization of galaxies into these complex networks is not a random occurrence, but a direct result of gravitational forces, which have been at work ever since the universe began expanding. This configuration strongly supports the notion that the universe had a singular beginning, originating from a point of immense density and heat, commonly known as the Big Bang. Since that moment, space itself has been stretching and expanding, setting the stage for the gravitational forces we observe today. The sheer scale of this cosmic expansion suggests that the universe continues to grow, evolving in ways that remain mysterious and awe-inspiring. As the universe expands, galaxies and other celestial objects continue to move apart, contributing to a universe that is constantly changing and becoming more diffuse. This constant movement of galaxies provides critical insight into the underlying forces that govern the evolution of our cosmos. Our understanding of the universe's expansion has transformed significantly since the early 20th century. Initially, the prevailing theory was that the universe was a static, unchanging entity. This notion was widely accepted until the 1920s, when the groundbreaking observations of astronomer Edwin Hubble revolutionized our understanding of the cosmos. Hubble discovered that distant galaxies were receding from us, and intriguingly, the farther away a galaxy was, the faster it seemed to move. This finding led to the realization that space itself was expanding. For the first time, scientists began to consider the universe as a dynamic, evolving entity. something that was not only changing, but was doing so at a vast and incomprehensible scale. This discovery sparked the development of the Big Bang theory, which posits that the universe began from a singular point in time and space, expanding outward in all directions. As scientists delved deeper into the implications of Hubble's observations, they found further support for this theory. One such key piece of evidence was the discovery of cosmic microwave background, CMB, radiation. This faint afterglow, still detectable today, is the remnant radiation from the very beginning of the universe, providing us with a snapshot of the cosmos as it was just moments after the Big Bang. In the late 20th century, our understanding of cosmic expansion took yet another leap forward with the discovery of dark energy, a mysterious force believed to be driving the accelerated expansion of the universe. This revelation fundamentally altered previous models of the cosmos. Whereas scientists once believed that the expansion of the universe would slow over time due to the pull of gravity, the discovery of dark energy suggested that, in fact, the expansion was speeding up. This has introduced an entirely new level of complexity to our understanding of the universe, raising questions about the ultimate fate of everything within it. Today, astronomers and physicists are still refining their models of the universe's expansion. Using cutting-edge tools and technology, they gather data from distant galaxies and analyze the light emitted by these far-off objects. By studying this light, scientists can discern subtle clues about the rate of cosmic expansion and how it has changed over time. Each new piece of information offers fresh insights into the universe's history and its ongoing evolution, but there is still much we do not know. The mysteries of the cosmos are vast and complex, and our journey to unravel them is far from complete. One of the greatest mysteries surrounding the expansion of the universe is its ultimate fate. As we observe the universe's ongoing expansion, we notice that galaxies are moving away from us, and the rate at which they do so seems to be accelerating. This expansion is believed to be driven by dark energy, an unknown force whose nature remains elusive. The question of what will happen to the universe in the distant future is one that has intrigued scientists and philosophers alike for centuries. As we ponder the future of the cosmos, several theories have emerged, each offering a different perspective on how the story of the universe might unfold. One possibility is that the expansion of the universe will continue indefinitely, leading to a scenario known as the Big Freeze. In this scenario, galaxies would drift farther apart, stars would burn out, and the universe would eventually become a cold, dark, and lifeless place. This slow and inexorable decline would result in a state of uniform coldness, devoid of light, energy, or matter as we know it. The Big Freeze paints a picture of a universe that, over unimaginable stretches of time, becomes increasingly desolate. Another possibility is the Big Crunch, where the expansion of the universe eventually slows and reverses. In this scenario, the force of gravity would overcome the cosmic expansion, causing everything to collapse inward toward a singular point. This would be akin to a cosmic yo-yo, pulled back into a dense, hot, and compact state. The collapse could potentially trigger another Big Bang, giving rise to a new universe, one that is born from the ashes of the previous cosmos. This cyclical model of cosmic birth and death suggests that the universe might be part of an endless cycle of expansion and contraction. A third, more dramatic theory is the Big Rip. In this scenario, dark energy would continue to accelerate the expansion of the universe to such an extent that it would eventually tear apart galaxies, stars, planets, and even atoms. The universe would undergo a violent and catastrophic end, where all the structures that define the fabric of space and time disintegrate into nothingness. This apocalyptic vision presents a universe whose future is marked not by a slow decline, but by a sudden, explosive end that would unravel the very nature of reality itself. Despite these theories, the nature of dark energy remains one of the greatest enigmas in modern cosmology. Scientists continue to gather data, examining the behavior of distant supernova and measuring cosmic microwave background radiation to learn more about this mysterious force. Yet, its true nature remains hidden, and until we unlock its secrets, predicting the future of the universe is a daunting task. Each of these theories carries profound implications, not just for the fate of galaxies, stars, and planets, but for the very fabric of space and time. In addition to these grand cosmic questions, the vast spaces between galaxies are home to a number of fascinating and mysterious structures. The intergalactic medium, the vast, largely empty space between galaxies, is far from a lifeless void. It is teeming with intriguing phenomena, many of which hold clues to the universe's past, present, and future. One of the most remarkable features of the intergalactic medium is the cosmic web. Imagine the universe as a massive spider's web, where galaxies serve as the knots, interconnected by strands of dark matter and gas. These vast filamental structures stretch across the cosmos, forming the large-scale structure that shapes the distribution of galaxies. Another intriguing aspect of the intergalactic medium is the presence of cosmic voids. These are enormous, mostly empty regions of space that can span millions to billions of light years. Within these voids, galaxies are sparse, and the emptiness is striking in contrast to the dense clusters of galaxies found in other regions. Understanding these voids is crucial to our understanding of the universe's large-scale structure, as they help define the boundaries between more densely populated areas and offer insights into the early stages of the universe's evolution. Intergalactic space is also home to ancient remnants of galaxies and stars, some of which have been ejected from their parent galaxies during violent events or gravitational interactions. These rogue stars, known as intergalactic stars, provide valuable information about the dynamic processes that govern galaxy formation and evolution. Investigating these lost stars helps scientists piece together the complex history of the universe and provides a window into the forces that shape galaxies over billions of years. Dark matter, a mysterious substance that does not emit light or energy, plays a crucial role in shaping the gravitational framework of the universe. Although we cannot directly observe dark matter, its influence is evident in the way galaxies move and cluster together. It acts as the invisible scaffolding that holds galaxies and larger structures together, even though it remains largely undetectable by conventional means. Dark matter is an essential component in the cosmic web, contributing to the formation of galaxies and the evolution of large-scale structures. Finally, intergalactic space is home to some of the most energetic and catastrophic events in the universe, such as gamma-ray bursts. These intense bursts of energy, which occur when massive stars collapse or when neutron stars collide, offer valuable clues about the processes that govern stellar life cycles. These high-energy phenomena also provide insight into the most extreme conditions of the universe and the fundamental forces that drive its evolution. Together, these structures and phenomena paint a picture of the intergalactic medium as a vast, complex, and dynamic environment. It is not just a region of emptiness, but a fertile ground for discovery, filled with hidden secrets waiting to be uncovered. As scientists continue to explore the intergalactic realm, they are unraveling the mysteries of the universe's past, present, and future, offering us glimpses into the grand story of cosmic evolution. The more we learn about the cosmos, the more we realize how much there is still to discover, making the journey of exploration an endless and exciting pursuit. Furthermore, phenomena such as gravitational lensing offer crucial insights into the cosmos. Gravitational lensing occurs when light from a distant galaxy passes near a massive object, like a galaxy cluster. The immense gravitational field of the object bends and magnifies the light, acting like a cosmic magnifying glass. This effect allows astronomers to peer into the intricate details of the galaxy cluster itself, and even more importantly, to study the invisible dark matter surrounding it. Dark matter, though undetectable through conventional means, exerts gravitational influence on visible matter, and its distribution plays a pivotal role in shaping the large-scale structure of the universe. By observing how light is distorted by gravitational lensing, scientists can infer a great deal about the amount and arrangement of dark matter in the universe, thus revealing essential information about the forces that govern cosmic behavior. In addition, the cosmic microwave background, CMB radiation, which represents the faint afterglow of the Big Bang, offers an invaluable snapshot of the universe's early moments. This radiation provides a direct link to the state of the universe when it was merely a fraction of its current size, just 380,000 years after the Big Bang. The CMB holds subtle fluctuations that reflect variations in density, which later evolved into galaxies and large-scale cosmic structures. Through detailed studies of the CMB, scientists can uncover clues about the conditions that led to the formation of the galaxies, the distribution of matter, and even the evolution of the universe itself. These early remnants of the universe offer a kind of time machine, allowing us to look back to the dawn of cosmic history, long before stars and galaxies even began to take shape. Intergalactic phenomena provide more than just a glimpse into the universe's large-scale architecture. They also deepen our understanding of the fundamental forces that govern it. Each observation of these phenomena adds a new piece to the cosmic puzzle, bringing us closer to a unified theory of how the universe came to be. Intergalactic events, such as the movements of galaxies, the collision of galaxy clusters, and the interactions of dark matter, constantly shape and reshape the very structure of the cosmos. These events reveal the dynamic and constantly evolving nature of the universe, offering not only a snapshot of its current state, but also insights into its past and future. The cosmic web, an immense, sprawling network of galaxies, galaxy clusters, and dark matter, serves as the large-scale structure of the universe. Picture it as an elaborate spider's web, with its intricate strands connecting galaxy clusters and dark matter nodes. Intergalactic events, including galaxy collisions, the formation of new galaxies, and the movement of dark matter, profoundly affect the evolution of this web. When galaxies collide, they don't simply crash into one another. Instead, they engage in gravitational interactions that trigger a variety of phenomena. One of the most spectacular outcomes of these collisions is the formation of new stars. As gas clouds are compressed and heated during these galactic encounters, they ignite bursts of star formation. These stars, in turn, alter the properties of the surrounding gas and contribute to the overall mass distribution of the galaxies involved. Moreover, such collisions can lead to the merging of entire galaxies, resulting in the creation of larger, more complex structures. These newly formed galaxies, with their stronger gravitational fields, attract additional matter and further contribute to the ongoing evolution of the cosmic web. This process illustrates how large-scale galactic events play a critical role in the growth and development of the universe's structure over time. Dark matter, a mysterious and invisible component of the universe, acts as a scaffolding that influences the distribution of visible matter throughout the cosmos. Though dark matter cannot be directly observed, its presence is inferred through its gravitational effects on galaxies and galaxy clusters. Intergalactic events, such as galaxy mergers or the movements of galaxies through dark matter fields, can alter the distribution of this elusive substance. These changes, in turn, influence how galaxies form and cluster together, shaping the growth of the cosmic web. Dark matter, which accounts for a significant portion of the universe's mass, plays a central role in the organization of the cosmos. Its influence on visible matter cannot be overstated, and understanding how dark matter interacts with other cosmic forces is key to unraveling the mysteries of the universe. Supernovae, the explosive deaths of massive stars, are yet another crucial phenomenon in the intergalactic landscape. These spectacular events release enormous amounts of energy, which can heat the surrounding gas, expelling it from the galaxy and altering its mass and structure. The energy produced by supernova also contributes to the intergalactic medium, an expansive region of hot gas that exists between galaxies. This process not only impacts the galaxy hosting the supernova, but also contributes to the overall dynamic of the intergalactic space, influencing the movement and interaction of matter across vast distances. Intergalactic events like these are essential in shaping both the formation and evolution of galaxies, as well as the larger cosmic web. They help mold the universe into its current structure, and their ongoing interactions create a dynamic, ever-changing cosmos. The interplay between galaxies, dark matter, and various cosmic phenomena highlights the complex, interconnected nature of the universe. It is this delicate balance that governs the growth and evolution of cosmic structures over billions of years. The concept of the cosmic horizon is an essential aspect of our understanding of the universe. This invisible boundary marks the limit of the observable universe, the farthest point from which light has had time to travel since the Big Bang. Imagine standing on a vast, flat landscape shrouded in a gentle fog. As you look out, there is a distance that you can see clearly, but beyond that point, everything fades away into the mist. The cosmic horizon operates in much the same way, forming an edge to the observable universe. Since the universe has been expanding since its inception, the distance of this horizon continues to increase over time. Light from distant objects that are beyond this limit has not had enough time to reach us, and thus remains unseen. This cosmic horizon creates a sort of visual border to our understanding of the universe. It defines the observable universe, beyond which lies a realm that is forever out of reach. Within this unobservable region could exist galaxies, stars, or even entire clusters of matter. Yet we will never know, as the light from these objects has no way of reaching us. This boundary underscores the sheer vastness of the cosmos and serves as a reminder of the limits of our current knowledge. While we can only observe a small fraction of the universe, advances in technology and new discoveries continue to push the boundaries of what we can understand. Scientists are particularly fascinated by the cosmic horizon because it represents the limit of human observation. Beyond this boundary, there are mysteries that could transform our understanding of existence. One of the most intriguing questions concerns dark matter. Though we cannot see it, dark matter is thought to make up a significant portion of the universe's mass. Understanding its properties could unlock insights into the very nature of cosmic structure. Another enigma is dark energy, a mysterious force believed to be responsible for the accelerated expansion of the universe. Dark energy was first identified when astronomers discovered that galaxies were moving away from each other at an increasing rate. Determining the nature of dark energy could reveal fundamental truths about the universe's ultimate fate. Furthermore, the existence of structures beyond the cosmic horizon raises fascinating questions. Could there be other galaxies or even entire universes beyond our own? The multiverse theory suggests that our universe might be just one of many, each governed by its own set of physical laws. If this is true, it challenges everything we know about space and reality itself. What's more, if multiple universes exist, could events in one universe interact with or influence events in another? These questions invite deep exploration and invite both scientific inquiry and philosophical reflection on our place in the cosmos. The origin of the universe remains one of the greatest mysteries of all. While current models suggest a rapid expansion following the Big Bang, the question of what triggered this event, or what came before, remains unresolved. The cosmic horizon may hold answers to these profound questions, offering tantalizing clues that drive scientific exploration and wonder. Each of these mysteries pushes the boundaries of human understanding and invites further inquiry into the nature of existence itself. Through the study of the cosmos, we seek not only to understand the mechanics of the universe, but also to uncover the deeper, more philosophical truths that lie beneath its vast, star-filled expanse. The concept of the multiverse expands our curiosity even further. Imagine that our universe is not unique, but part of a larger, infinite system of universes. Each of these universes may have its own cosmic horizon, limiting what can be observed and known within its bounds. This raises the tantalizing possibility that our observable universe is just one small piece of a much greater, far more intricate reality. If we accept the possibility of the multiverse, it could mean that everything we know about the universe, its laws, its history, and its future, is only part of a much larger story. The concept of the cosmic horizon invites us to contemplate the vast limits of our understanding of existence. While our ability to explore the universe has expanded dramatically, the multiverse theory pushes the boundaries of our imagination even further, suggesting the possibility of realms beyond what we can observe or even comprehend. It paints a tantalizing picture, one that invites us to question the very nature of reality, hinting at a far grander cosmos than we currently perceive. Our current technologies, though advanced, still only scratch the surface of what may exist beyond the observable universe. We stand at the edge of discovery, with the potential to uncover mysteries that challenge everything we think we know. In this exploration, technology plays an indispensable role. It is not merely a collection of tools, but a bridge to a deeper understanding of the cosmos. Over the centuries, Our telescopes have transformed from simple lenses into highly advanced instruments capable of detecting light from stars and galaxies billions of light years away. These telescopes allow us not only to see these distant objects, but also to study their properties, such as their composition, age, and the vast distances that separate them from our small corner of the universe. With this ability, we can peer into the past, observing light that has traveled across space for millions, sometimes even billions of years before reaching our eyes. But telescopes alone are not enough. Space probes and rovers are our robotic explorers, sent to distant realms where human hands cannot yet reach. These machines gather invaluable data by traveling across the surfaces of distant planets or venturing through the icy regions of comets and asteroids. They monitor temperature, radiation, and even seek out signs of water, an essential ingredient in the search for life beyond Earth. Every bit of data they collect is a piece of a larger puzzle, one that could eventually reveal whether life exists elsewhere in the universe. Moreover, the rapid evolution of computer technology has revolutionized the way we process astronomical data. High-powered algorithms, artificial intelligence, and machine learning empower scientists to sift through enormous datasets, identifying patterns that would be impossible for humans to detect on their own. These advancements allow for faster discoveries, with each breakthrough leading to even more questions and more avenues of exploration. The scope of our inquiries is expanding, and technology is the engine driving this expansion. In addition to these groundbreaking developments, innovations in communication technology have also played a key role. As our space missions venture further into the cosmos, maintaining communication with spacecraft becomes increasingly difficult due to the vast distances involved. However, with the advent of satellite constellations and emerging quantum communication methods, the transmission of data over unimaginable distances is becoming more feasible. These advancements allow scientists to maintain real-time contact with distant explorers, whether human or robotic, ensuring that no matter how far we travel, we can stay connected to the far reaches of space. Looking to the future, space exploration stands on the precipice of revolutionary changes. Propulsion technology, for example, is poised for a transformation that could radically alter our approach to space travel. Imagine spacecraft equipped with engines capable of accelerating to a significant fraction of the speed of light. This would allow us to reach other stars within the span of a human lifetime, something that has long seemed like the stuff of science fiction. It would open the door to missions that could explore distant planets in other star systems, revealing new worlds and expanding our understanding of the universe in ways previously thought impossible. Another exciting development lies in the realm of robotics and artificial intelligence. Future spacecraft could be equipped with highly advanced robots capable of performing complex tasks such as repairing equipment or conducting scientific experiments on faraway planets. These autonomous systems would allow for longer missions and exploration of environments too dangerous or distant for human astronauts. With the power of AI, these robots could learn and adapt to new challenges, pushing the boundaries of what robotic exploration can achieve. At the same time, advancements in material science are opening new doors for spacecraft construction. Imagine ships built from materials that are not only lighter, but also far more durable, capable of withstanding the extreme temperatures, radiation, and other harsh conditions of space travel. These innovations would not only extend the longevity of missions, but also make deep space exploration more feasible, allowing for sustained travel to the outermost regions of the solar system and beyond. Renewable energy is another critical component for the future of space exploration. Solar power, once thought to be the primary means of fueling space missions, could soon be supplemented by nuclear energy, offering a sustainable solution for long-duration missions. This would reduce our reliance on traditional fuel sources and make it possible to establish bases on the Moon, Mars, or even farther afield, transforming our ambitions into tangible realities. In parallel, breakthroughs in communication technology are reshaping how we interact with space missions. As we venture further from Earth, maintaining real-time contact becomes increasingly difficult. But new satellite constellations and quantum communication systems are making this challenge more manageable. These advancements promise to keep our links with astronauts and robotic explorers intact, no matter how far they travel, ensuring that we can continue to learn from them and guide their journey across the cosmos. These technological advancements collectively paint a vision of a future where space travel is no longer a distant dream, but a practical and achievable reality. As our tools and capabilities continue to evolve, we can look forward to opening new frontiers, exploring uncharted territories, and deepening our connection with the universe. The search for extraterrestrial life is intricately connected to the rapid advancements in technology. The development of powerful telescopes has given us the ability to observe distant stars, searching for planets that might be capable of supporting life. Some of these planets are located in what scientists call the habitable zone, where conditions might be just right for liquid water to exist, an essential ingredient for life as we know it. But it's not just about observing these distant worlds. Technology has also enabled spacecraft to travel to nearby planets and moons like Mars and Europa to gather first-hand data about their atmospheres, surfaces, and potential for hosting life. Artificial intelligence and machine learning have become essential tools in processing the vast amounts of data generated by telescopes and space probes. These technologies can help identify potential candidates for further investigation by finding patterns that might otherwise go unnoticed. They also help us filter through years of collected data to focus on the most promising leads. In the search for extraterrestrial intelligence, radio telescopes have been used to listen for unusual signals that might indicate the presence of intelligent civilizations. Through advanced signal processing, scientists are now better able to differentiate between natural cosmic noise and possible messages from other life forms. The search for extraterrestrial life is not just a scientific pursuit. It's a deeply human one, driven by curiosity and the desire to understand our place in the universe. Each technological breakthrough brings us one step closer to answering the age-old question: are we alone? In many ways, science fiction has been a powerful influence on the way we approach space exploration. From classic tales of space travel to stories of first contact with alien civilizations, science fiction has sparked the imaginations of generations of scientists, engineers, and dreamers. It has inspired real-world technological advancements, pushing the limits of what is possible. The dream of traveling to distant planets and communicating with extraterrestrial beings, once relegated to the realm of fiction, is now becoming an ever more tangible goal. The Apollo moon missions, for example, were inspired by science fiction stories long before humans set foot on the lunar surface. These fictional works created a vision of what the future could hold, and that vision became the driving force behind real-world advancements. As we continue to push the boundaries of space exploration, it's clear that both science and science fiction will continue to shape our journey. Each new discovery, each breakthrough in technology, brings us closer to a future where the cosmos is no longer a distant, unknowable frontier, but a place where humanity can venture, explore, and perhaps one day even call home. Science fiction, more than just a genre of storytelling, has evolved into a vital avenue for exploring ideas about life beyond Earth and the broader mysteries of the cosmos. It raises profound questions about humanity's place in the universe, sparking curiosity about how we might adapt to alien environments and survive on distant planets. For decades, narratives within this genre have captivated minds, particularly with visions of humans navigating the harsh terrains of planets like Mars, where survival requires innovative solutions. As these fictional tales delve into the technological, social, ethical, and philosophical aspects of space exploration, they offer a unique lens through which to examine humanity's future. They provoke rich discussions among scientists, ethicists, and the public about the implications of venturing beyond our home planet. Interestingly, some of the most advanced technologies, once considered purely the stuff of fantasy, are now becoming tangible aspects of our scientific endeavors. Concepts such as robots and artificial intelligence, AI, in space were born from the imaginative pages of science fiction. Today, these ideas are being incorporated into real-world space missions, serving as practical tools in our quest to explore the final frontier. The growing intersection of imagination and innovation highlights how these once visionary concepts are now central to space exploration. When scientists develop new devices for exploration, they often reflect on the visionary ideas that first appeared in fiction, ideas that have since been transformed into critical components of our technological progress. Science fiction not only mirrors our dreams of the cosmos, but also acts as a guide to achieving them. These stories, filled with imagination and wonder, push humanity to strive for the stars and beyond. It's not just about creating new inventions, it's about igniting a deep, insatiable curiosity and a sense of awe that drives scientific and technological advancements. This drive is not merely a byproduct of practical necessity, it is a fundamental motivator for progress. Imagination becomes the catalyst for human endeavor, encouraging us to envision a future that is not yet realized, but is very much within reach. Imagination plays an integral role in fueling scientific inquiry, often acting as the spark that ignites curiosity. It pushes scientists to envision possibilities that stretch beyond current understanding, urging them to ask bold questions that challenge established knowledge. In a sense, it's like standing on the surface of an ocean, seeing only what is visible above the water. Imagination allows us to dive into the depths, exploring the unseen currents and creatures below. It's through this creative thinking that scientists begin formulating hypotheses, often proposing scenarios that have not yet been tested or observed. These speculative ideas can lead to experiments that ultimately unravel some of the deepest mysteries of the universe. Take, for example, the concept of black holes. The idea wasn't a direct result of established knowledge. Rather, it arose from an imaginative leap about how gravity might behave under extreme conditions. This leap in thinking opened the door to a new understanding of the cosmos, laying the foundation for further exploration into the nature of space, time, and gravity. Without the imaginative spark, concepts like black holes might never have seen the light of day. Similarly, when scientists began to understand atomic structure, they didn't simply confirm existing knowledge. They had to imagine, visualize atoms as tiny spheres. This imaginative notion led to profound breakthroughs in chemistry and physics, culminating in a much deeper understanding of how matter behaves on a microscopic scale. Beyond theoretical exploration, imagination is crucial in the development of innovative technologies. Think about the creative vision required to design a space telescope or a robotic explorer. These sophisticated tools, which allow us to peer into the farthest reaches of space, would not exist without the imaginative minds of scientists. They give us the ability to explore parts of the universe that would otherwise remain beyond our grasp. Technologies such as these expand our knowledge, enabling us to see and understand the universe in ways previously thought impossible. Without the imaginative drive that fuels these innovations, many of the technological advancements we now take for granted, such as the devices that allow us to communicate across vast distances or travel to other planets, would never have come into existence. Ultimately, imagination serves as a bridge between what we know and what we have yet to discover. It encourages bold exploration and tells us that the limits of scientific inquiry are not fixed, but are always expanding. As we continue to push the boundaries of what is possible, it is this imaginative spirit that unlocks the potential for groundbreaking discoveries, capable of reshaping our understanding of the universe itself. Artists and writers, too, play an indispensable role in shaping how we perceive the mysteries of the universe. Through their creative works, they transport us beyond the confines of everyday experience and introduce us to new, often unimaginable realms. In the realm of science fiction literature, readers are invited to explore the concept of space travel, encounter alien life, and grapple with questions of humanity's place in the vast expanse of the cosmos. These works blend scientific possibility with artistic creativity, fostering a sense of wonder that sparks curiosity about what lies beyond our planet. They often ask profound questions about the future of humanity, forcing readers to contemplate the ethical, social, and philosophical dimensions of space exploration. Visual artists also contribute to this exploration by interpreting astronomical phenomena through their creative expressions. Paintings, sculptures, and digital art can bring celestial bodies like stars, planets, and galaxies into vivid focus, allowing us to appreciate their beauty and complexity. These visual representations inspire awe and wonder, inviting us to connect with the cosmos in a more intimate, emotional way. By capturing the essence of distant worlds, artists offer a unique perspective on the universe that complements the more analytical approach of scientists. In doing so, they invite viewers to experience the universe not just as a collection of scientific data, but as a source of deep emotional and existential reflection. Poetry and literature also delve into profound themes such as time, existence, and the human experience against the backdrop of the cosmos. These works often explore the bigger questions of life, inviting readers to reflect on the nature of reality itself. In this way, art and literature make science more accessible, offering a lens through which the public can engage with complex ideas about space, time, and the fundamental forces of the universe. Through this fusion of creativity and scientific exploration, artists and writers serve as a bridge between the realm of scientific knowledge and the realm of human experience. They allow us not only to understand the mysteries of the universe, but to feel them deeply. As science continues to uncover the intricacies of the universe, new quantum phenomena and cosmic mysteries emerge. At the quantum level, particles such as electrons and photons behave in ways that defy traditional physics, existing in multiple states at once or becoming instantaneously connected across vast distances, a phenomenon known as entanglement. This behavior challenges our understanding of reality itself, raising questions about the very nature of existence. Even when we turn our gaze to the vast expanse of the cosmos, these quantum phenomena may play a crucial role. Some scientists suggest that quantum fluctuations, which occur at the smallest scales of reality, could have influenced the formation of galaxies and large-scale structures in the universe. In fact, some theories propose that the early moments of the universe, just after the Big Bang, were governed by quantum mechanics. This period of quantum activity could have sparked the rapid expansion and evolution that led to the universe we observe today. As our understanding of quantum mechanics continues to deepen, it may hold the key to unlocking some of the greatest mysteries of the universe, offering insight into the very fabric of space and time. In conclusion, the relationship between science fiction, imagination, and scientific progress is both profound and intertwined. Science fiction continues to fuel our dreams and ambitions for space exploration, while offering a space for creative minds to ponder what lies beyond. Imagination, the engine driving scientific inquiry and technological innovation, remains a powerful force that shapes the future. And as we continue to push the boundaries of knowledge, we are reminded that both art and science are essential in guiding us toward new discoveries, allowing us to explore and appreciate the vast, mysterious universe we are only beginning to understand. The vast expanse of the cosmos holds many secrets, some of which may forever elude our understanding. However, there are profound connections between the smallest particles and the greatest celestial bodies, both of which are governed by the same underlying principles. One of the most intriguing and enigmatic aspects of our universe lies in the phenomena of dark matter and dark energy. Although we cannot see dark matter directly, its presence is unmistakably inferred through its gravitational effects on galaxies and large-scale structures in the universe. Some groundbreaking theories propose that the particles making up dark matter may follow quantum mechanical rules, behaving in ways that we have yet fully comprehend. This theory suggests that dark matter may interact in ways that are radically different from what we have traditionally understood, leaving a tantalizing gap in our knowledge waiting to be filled. In parallel, dark energy, the mysterious force that drives the accelerated expansion of the universe, may also have its roots in quantum mechanics. This connection could unveil a deeper, more profound relationship between the microcosmic world of particles and the vast expanses of space itself. If dark energy is indeed linked to quantum forces, it could point toward an intricate dance between the infinitesimally small and the impossibly large, suggesting that the rules of quantum mechanics do not only govern the particles that make up the very fabric of matter, but also the grandiose movements of galaxies. As we delve into these theories, we find ourselves confronting questions that challenge the very essence of what we know about the universe, space, and time. This intersection between the quantum realm and cosmic phenomena forces us to reconsider everything we know about the universe. It compels us to expand the boundaries of science, philosophy, and even our deepest perceptions of reality. The more we investigate these phenomena, the more we realize that the universe might be a vast, intricately woven tapestry, composed not only of vast cosmic structures, but also of the tiny particles that define the very foundation of all matter. Each part influences the other in ways that are just beginning to be revealed. By exploring these connections, we begin to understand that the universe may be far more interconnected and mysterious than we ever imagined. Quantum mechanics, with its puzzling and paradoxical phenomena, challenges everything we thought we knew about reality. One of the most mind-boggling concepts in this field is quantum entanglement. This phenomenon occurs when two particles become entangled, such that the state of one instantly influences the state of the other, regardless of the distance between them. This concept goes against everything we know about classical physics, which states that information can only travel through space at a finite speed. Quantum entanglement raises profound questions about the nature of space, time, and information itself. Scientists are now exploring how this strange connection between particles could be harnessed for applications such as secure communication and advanced computing, paving the way for revolutionary technological advancements. Equally puzzling is the concept of superposition, a principle that suggests that particles can exist in multiple states or locations simultaneously. Only when observed does the particle collapse into one definite state. This concept forces us to question the very nature of reality and observation. What does it mean to observe something? How does the act of measurement affect the state of the world around us? As researchers probe deeper into this phenomenon, they are uncovering new insights into the relationship between observation, consciousness, and the physical world. Then there is the paradox of wave-particle duality, a strange behavior exhibited by particles like electrons and photons. These particles can show characteristics of both particles and waves, depending on how they are observed. This duality shakes the foundations of how we define matter itself. If particles can behave as both waves and particles, what does that mean for our understanding of the very nature of the universe? It challenges us to rethink the fundamental definitions of matter and energy, and invites us to expand our understanding of the microscopic world. Moreover, as we venture deeper into the mysteries of quantum mechanics, we begin to confront profound questions about the very fabric of space and time. The concept of quantum foam suggests that at the smallest scales, space and time are not smooth and continuous, but instead are jittery and chaotic, resembling a frothy, bubbling texture. This insight has far-reaching implications, particularly for our understanding of gravity and the early moments of the universe. If space and time themselves are not what they appear to be at quantum scales, it could lead to new theories of gravity, providing deeper insights into the very origin of the cosmos. Investigating these quantum mysteries is more than just an academic pursuit. It has the potential to unlock entirely new technologies and change the way we perceive the universe itself. Each new discovery opens doors to further exploration and provides clues about the true nature of reality. Every breakthrough, no matter how small, has the power to shift our understanding of how the universe works, leading to advancements in everything from computing to communication to our understanding of the cosmos. At the heart of quantum theories lies the idea that everything in the universe is made up of tiny particles, many of which behave in ways that defy classical physics. These particles interact with each other in ways that seem random and unpredictable, but quantum mechanics holds the key to understanding this apparent randomness. By applying quantum principles to some of the greatest cosmic mysteries, scientists are beginning to uncover how quantum mechanics might explain some of the universe's greatest puzzles, such as the nature of dark matter and the behavior of black holes. Dark matter, for example, is an invisible substance that makes up a significant portion of the universe's mass. Despite its enormous influence on the structure and behavior of galaxies, we have yet to detect it directly. Some quantum theories suggest that dark matter particles might exist in states that we have yet to fully understand, opening up new avenues of research into their nature and properties. By studying how these particles might behave, scientists hope to reveal how dark matter shapes the structure of the universe and the behavior of galaxies. Similarly, quantum mechanics may offer new insights into the nature of black holes, those mysterious regions of space where gravity is so intense that not even light can escape. In classical physics, black holes were thought to be regions where all information about the matter that falls into them is lost. However, recent quantum theories propose that information might not be permanently destroyed inside a black hole, but could be preserved in some form. This revelation challenges traditional notions about the nature of space, time, and information, and could reshape our understanding of how black holes function and how they fit into the larger structure of the universe. As scientists continue to explore these quantum theories, they may uncover even deeper connections between the quantum world and the cosmos. These discoveries could lead to new technologies and techniques that revolutionize our understanding of space and time, shedding light on some of the most perplexing mysteries of the universe. The quest for a theory of everything is perhaps the most ambitious endeavor in modern science. This theory aims to unify all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single coherent framework. Such a theory would provide a seamless understanding of the universe, from the smallest particles to the largest galaxies, and would revolutionize our understanding of how everything in the universe works. Currently, we have separate theories for gravity, which governs the motion of planets and galaxies, and quantum mechanics, which describes the behavior of particles on the smallest scales. While these theories work well within their domains, they clash when we attempt to apply them together, especially in extreme conditions like those found near black holes or during the Big Bang. A theory of everything seeks to resolve these contradictions and provide a unified framework that explains how the universe operates at all levels, from the infinitesimal to the cosmic. As scientists continue their search for this elusive theory, they are pushing the boundaries of human knowledge, attempting to answer some of the most profound questions about the nature of reality itself. If successful, a theory of everything could provide the ultimate understanding of the universe, offering insights into its origins, its structure, and its ultimate fate. It may also lead to a future where we can manipulate the very forces that shape our reality, bringing about breakthroughs that will forever change our understanding of the cosmos. Moreover, these theoretical frameworks hold the potential to bring about revolutionary transformations in technology, medicine, and our fundamental understanding of existence itself. The search for a unified theory which could tie together the various forces of the universe is not simply an intellectual pursuit. It is a quest that has the power to reshape our world. As we stand on the edge of this pursuit, we are reminded that the drive to understand the universe's deepest secrets pushes the limits of human knowledge, opening doors to new possibilities that could redefine everything from our relationship with the cosmos to the very fabric of reality. The exploration of a theory of everything is, at its core, a reflection of humanity's deepest desires to grasp the hidden laws governing existence and, perhaps, uncover our place in the vast universe. At the heart of this search lies the unified theory of physics, a journey into understanding how the fundamental forces of nature operate in harmony. In our current understanding, we recognize four primary forces that govern the cosmos: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces plays a critical role in shaping the structure of the universe, from the orbits of planets to the behavior of atoms. However, they operate within distinct realms, each with its own set of rules and limitations. Despite these distinctions, the goal of modern physics is to unite these forces under a single framework, one that would explain their relationships and offer new insights into the universe's hidden workings. In recent years, tremendous progress has been made in this field, particularly with the advent of string theory. This groundbreaking concept posits that the very building blocks of the universe are not point-like particles as traditionally thought, but rather tiny, vibrating strings. These strings are believed to exist in multiple dimensions, more than the 3 dimensions of space and 1 of time that we experience in our everyday lives. The existence of these extra dimensions offers a radically new way of thinking about how forces interact with one another. String theory, while still in its infancy, presents a promising path toward unification, offering the tantalizing possibility that all the fundamental forces could stem from a single unified source. Another exciting theoretical framework is loop quantum gravity, which seeks to bridge the gap between general relativity, the theory that describes the force of gravity, and quantum mechanics, the theory that governs the behavior of particles at the smallest scales. Loop quantum gravity suggests that space itself is not a continuous, smooth fabric, but instead is made up of tiny, discrete units. In this model, the very fabric of space-time is quantized, much like the way matter is made up of atoms. If this theory holds true, it could revolutionize our understanding of the universe's most fundamental structure. While these theories are compelling, they remain speculative. To confirm or challenge them, scientists rely heavily on experimental data, much of which comes from high-energy particle accelerators like the Large Hadron Collider. These accelerators smash particles together at incredible speeds, allowing researchers to study the fundamental interactions that occur at these extreme conditions. By analyzing the results of these experiments, physicists hope to uncover evidence that could either support or refute the various theories of everything. So far, the data has provided valuable insights, but the ultimate answer remains elusive. Even without a fully accepted theory of everything, the pursuit itself serves as a testament to humanity's unwavering curiosity. Each discovery, whether it affirms existing ideas or opens new avenues of inquiry, is a step closer to understanding the vast mysteries of the universe. As scientists continue to probe the unknown, every new piece of data brings us closer to a more complete picture of how the universe operates and how the forces that shape it are intertwined. A theory of everything is, essentially, an attempt to weave together the various threads of our current understanding, gravity, electromagnetism, quantum mechanics, into a single cohesive framework. At present, our understanding is fragmented, with each of these theories excelling in its specific domain but struggling to connect with the others. Gravity, for instance, describes the behavior of massive objects like planets and stars, while electromagnetism governs the interactions of charged particles. Quantum mechanics, on the other hand, excels at explaining the behavior of subatomic particles. Yet these 3 theories exist in isolation from one another, with no overarching framework to link them together. To illustrate this, one could imagine that our current theories are like individual pieces of a massive puzzle. Each piece provides a glimpse of the bigger picture, but without the others, they fail to reveal the full image. The theory of everything seeks to connect these disparate pieces, offering a comprehensive understanding of how all the forces and particles in the universe are connected. If successful, this unified theory could offer profound insights into some of the most perplexing mysteries of modern science, including the nature of dark matter, dark energy, and the origins of the cosmos itself. If such a theory could be realized, it would not only enhance our understanding of the universe's past, but could also offer predictions about its future. For example, a unified theory might shed light on whether the universe will continue expanding forever, or if it will eventually collapse in on itself. This knowledge would transform our conception of reality, offering a vision of the universe as a dynamic, interconnected system, one in which everything from the smallest particles to the grandest galaxies is part of a greater cosmic dance. The search for a theory of everything is more than an intellectual exercise. It represents a deep human yearning to understand our place in the universe. Cosmic phenomena like stars, galaxies, and black holes have long captured our imaginations, inspiring a desire to explore the unknown. When we gaze up at the night sky, we see an endless expanse of twinkling lights and wonder about their origins, their purpose, and the possibility that we are not alone in the universe. This sense of awe drives us to explore, to seek answers to questions that stretch far beyond the bounds of our everyday lives. Additionally, cosmic events like supernovae, stellar explosions that mark the death of massive stars, or the merger of galaxies remind us of the raw power and beauty of nature. These events, while destructive, also give birth to new elements and new stars, contributing to the ongoing evolution of the universe. They also serve as a reminder of our own place in this vast cosmic tapestry, encouraging us to push the boundaries of science and technology in order to better understand the world around us. The challenge of space exploration also plays a critical role in driving innovation. Endeavors like sending humans to Mars or exploring the outer reaches of our solar system require unprecedented cooperation between nations and researchers. They demand the development of new technologies and the overcoming of challenges that just a few decades ago seemed insurmountable. But these challenges also offer tremendous rewards, not just in terms of scientific knowledge, but in the development of technologies that can enhance life on Earth. From advancements in materials science to innovations in communication and computing, the pursuit of space exploration has led to countless breakthroughs that have practical applications in our daily lives. But the search for knowledge does not stop at the physical boundaries of our world. As we push forward in our quest to understand the cosmos, we also seek to understand the fundamental mysteries that underpin the fabric of the universe itself. Among these mysteries, dark matter is perhaps one of the most enigmatic. Though it makes up a significant portion of the universe's mass, it neither emits nor absorbs light, making it invisible to our most powerful instruments. We know it exists only because of its gravitational influence on visible matter, yet its true nature remains unknown. In a similar vein, dark energy, the mysterious force responsible for the accelerated expansion of the universe, has left scientists puzzled. While we are aware of its presence through the effects it has on the universe's expansion, we know little about what it actually is. What we do know is that it constitutes the majority of the universe's energy content, and its properties could hold the key to understanding the ultimate fate of the cosmos. Black holes, too, present profound challenges to our understanding of physics. These regions of space possess such intense gravitational fields that nothing, not even light, can escape their grasp. The nature of black holes, particularly their intersection with both general relativity and quantum mechanics, continues to raise difficult questions about the very fabric of space and time. What happens inside a black hole? Can information be lost forever? Or is it preserved in some form? These questions continue to fuel the curiosity of scientists, and each new discovery brings us one step closer to understanding one of the most perplexing phenomena in the universe. In the end, the pursuit of a theory of everything is not just an academic challenge. It is a profound journey into the heart of reality itself. It is a quest to understand the forces and particles that govern the universe, and perhaps to uncover the true nature of existence. Each new discovery, whether it affirms our current theories or challenges them, brings us closer to the ultimate goal, a unified understanding of the cosmos that could transform our perception of the universe and our place within it. Gravitational waves represent a profound enigma, one that continuously reshapes our understanding of the cosmos and serves as a beacon for further exploration in the realm of modern physics. These ripples in spacetime, which were first detected in 2015, are caused by some of the most cataclysmic events in the universe, such as the collision of black holes or the merging of neutron stars. Their discovery, almost a century after Albert Einstein first predicted them in his general theory of relativity, not only validated his groundbreaking theories, but also unlocked entirely new pathways for us to observe and understand the universe. The detection of gravitational waves marked a pivotal moment in astronomy, allowing us to peer into the fabric of spacetime itself in ways that were once thought impossible. Prior to this, our knowledge of the universe was limited to what could be observed through light, whether visible or in the form of other electromagnetic radiation. Now, with the advent of gravitational wave astronomy, we have an entirely new dimension of data that promises to reveal previously invisible phenomena. Events like the collision of black holes, each one containing a mass many times greater than that of the Sun, are now within our observational reach, providing a more detailed and dynamic view of the most extreme and mysterious processes that shape the universe. This discovery does not merely expand the tools at our disposal, it transforms our fundamental approach to exploring and understanding the cosmos. But gravitational waves are not the only frontier in this age of discovery. The search for extraterrestrial life, a pursuit that has long captivated the human imagination, is perhaps one of the most tantalizing and profound quests in modern science. For centuries, the possibility of life beyond Earth has been a subject of myth, speculation, and philosophical wonder. Yet, as our technology advances and our capacity to explore other planets increases, the question no longer remains confined to the realm of science fiction. With the discovery of exoplanets, planets that orbit stars outside of our solar system, astronomers now believe that the conditions for life might not be as rare as once thought. These distant worlds, some located in what's known as the habitable zone, where liquid water could exist, fuel a growing excitement in the scientific community. Could microbial life, adapted to harsh environments far different from our own, exist on these distant planets or moons? If life can thrive in conditions previously thought inhospitable, what does that say about the adaptability and resilience of life itself? The implications of such discoveries are profound, not just scientifically, but philosophically, as they challenge our definitions of biology and the very nature of life. Equally, the search for extraterrestrial life forces us to confront deeper questions about the uniqueness of humanity and our role in the universe. If we are not alone, how does that alter our understanding of our existence? Are we simply an accident of cosmic chance, a random occurrence in an unimaginably vast universe, or is there something more significant at play? These questions, once confined to the pages of philosophical texts and science fiction, are now becoming a legitimate part of scientific discourse, urging us to rethink our place in the grand cosmic tapestry. Then, there is the profound philosophical impact of the discoveries that continue to shape our understanding of space and time. The detection of gravitational waves, alongside other breakthroughs like the discovery of black holes, forces us to reconsider some of the most fundamental assumptions of our reality. Black holes, for instance, are regions of space where gravity is so intense that not even light can escape. They challenge our understanding of time and space itself, warping both in ways that were once purely theoretical. The realization that time itself can behave differently in these extreme environments stretches the boundaries of human comprehension and prompts us to ask even deeper questions about the nature of reality. Is time, as we experience it, an illusion? And if so, what does that mean for our understanding of existence? The search for answers to these cosmic mysteries is not just a scientific endeavor, it is also a philosophical one. Every discovery, every new insight into the workings of the universe prompts us to reflect on our own existence. The vastness of space, with its billion-year-old stars and galaxies, can make human life seem insignificant in comparison. Yet, paradoxically, this realization also magnifies our desire to understand, to search for meaning in the immensity of the cosmos. It drives us to explore, to innovate, and to push the boundaries of what we know. We look to the stars, not only to answer questions about the nature of the universe, but also to better understand who we are and why we are here. In the end, these cosmic mysteries are far more than just scientific puzzles. They invite us to think about the very essence of reality, our place in the universe, and the potential for discovery that lies ahead. As humanity continues its journey of exploration and innovation, the possibilities seem endless. Each new discovery, whether it's the detection of gravitational waves or the search for extraterrestrial life, offers a glimpse into the deeper workings of the universe, a universe that is far more complex and wondrous than we ever imagined. And as we stand at the precipice of these groundbreaking revelations, we can't help but feel a sense of awe and anticipation for what lies beyond the horizon of our current understanding.